everyone. So we're about to start. So I'll be your host for today. My name is François-Xavier Briol, FX for short. I think most of you probably know me already. So today we'll start with Nicolas Chopin. So Nicolas is a professor at ENSAE and Institut Polytechnique de Paris. He's going to talk to us about high-order stochastic integration through cubic stratification. I'll give you some 5-minute warning before the end of the talk.
All right. How much time do I have?
I think 45 minutes. 45
minutes and you
yes.
can, okay. Right, okay.
Thank you. Go ahead.
Thank you very much. Thanks for inviting me. It's always a pleasure to come to London. I'm sorry if some of you have seen this talk before. I'm just loved giving this talk because it's a piece of work I really enjoyed doing with my colleague Mathieu Gerber from Bristol University. And some of the basic ideas are extraordinarily simple. Essentially, you need to know about expectation, Taylor expansion, basic stuff. And also it involves some kind of forgotten ideas or results from the 50s, 60s, which was, it's a bit of a shame that it has been forgotten. I was surprised I would learn about it only today, right? So to whet your appetite with this n-5 error rate, which is really fast, and you will see that it's not a lie. I mean, you can get this kind of rate for certain cases, all right? So again, as I said, this is joint work with Mathieu from Bristol, 2 hours from here. And I will spend quite a lot of time on generalities on random algorithms that return random output for quadrature, computing integrals, and the base rate you can achieve. And I should have time also to discuss 2 new estimators that we are proposing with Mathieu. So any question? Again, the basic ideas are quite simple. So if there's anything unclear, it's my bad. I mean, I'm not explaining things well. Feel free to interrupt. I'm happy to re-explain. Okay. Right. So quadrature, or please, yeah. I have some function f defined of a 0, 1 power of s, so in dimension s. Yeah, for some reason in that area, people use S instead of D, not my choice. But, and you want to compute its integral, okay? And to do so, you're ready to pay the following price and evaluation of F, all right? And so a random quadrature algorithm is an algorithm that is going to return essentially an estimate, random output, which is close to this quantity of interest. And a standard criterion to evaluate your algorithm will be the root mean square error, which is the square root of this quantity. Okay, so this is the error, the difference between your estimate, the random output of your algorithm, and the true quantity. You take the square of this, and you take the expectation. Again, accounting for the fact that your output is random, all right? I use the word estimate from Statistique or estimator, and this word exactly match what I'm trying to do here. But otherwise, in this literature, they would say random algorithm, etc. We will focus on unbiased estimate, which means that this random quantity already has the correct expectation. In this case, the mean square error equals the variance. Before you take the square root. So equivalently, I'm trying to find an algorithm with a small variance, the smallest possible, okay? I'm focusing on unbiased estimate for several reasons, which are a bit obvious, but I think it's worth re-explaining why. If I can get an unbiased estimate, I can generate k-independent estimates. Maybe I can do that in parallel. Okay, which is really something which is getting easier and easier to do. And if I have k estimates obtained in parallel or not, it's easy to assess the numerical error. I just compute the empirical variance, all right? That's obvious, but that's really important in practice because other means of approximation don't have this property, okay? Maybe you have a deterministic approximation, but no way of evaluating the error. And here you have this very simple approach. And if you compute the average of your independent estimate, its variance will be divided by a factor of k. So you're not wasting your time by doing this replicates, you're also further reducing the variance, okay? All right. Also, in this area, we could distinguish between random algorithms and deterministic algorithms, but people, even people who are not from statistics, etc., are just looking at this quadrature problem in general. They say they prefer random algorithms because they have better rates. Okay, so that's all the reason why you want to do something random and unbiased. That's very nice properties. Anyway, this is Monte Carlo, the most obvious approach you're already familiar with. Here you can see I simulate n times from the uniform distribution independently in 0, 1 power s again. This is easy to do. And I evaluate f n times and compute the average. And it's easy to check that the root mean square error is of order 1 over the square root of n minus 1/2. Okay. So this is obvious. This is like the Monte Carlo algorithm that you maybe teach to your students if you're teaching. But there's still this open question. Can you, based on the same budget, could you get better rates of convergence? The answer is yes, if you're ready to focus on a smaller class of function. Because the big advantage of Monte Carlo, of course, is that the only assumption you need to make it work is that the moment of order 2 is finite. So that's a very large class of function, okay? But you can get better rate at a price of a smaller class of function. By smaller class of function, I will talk about functions that are regular in some way. At this point, you might think, oh, he's going to talk again about quasi-Monte Carlo, blah, blah, blah. Quasi-Monte Carlo is great, but the funny thing about this, I'm pretty new to this area, so I'm still happily surprised by some discoveries. And the happy surprise here is that this has nothing to do with quasi-Monte Carlo. You can do all of this business of defining and developing unbiased estimate with better rate without touching quasi-Monte Carlo in any way. Or maybe you could call what we're doing quasi-Monte Carlo, but it's a different thing. People who knew about all the things I'm going to tell you are put in the quasi-Monte Carlo or randomized quasi-Monte Carlo community, but still it's a different beast in my view. Right, so we reach the stage where I expect most of you didn't know about this before. I didn't until recently. And so this Russian guy, Bakvalov, which in 1959, he established the following result. If you're ready to assume that f is r times continuously differentiable, so regularity of order r, so to speak, okay? You can show that the best you can do is this rate for a random algorithm, right? N minus 1/2 minus r over s, okay? So there's a curse of dimensionality. When the dimension is increases, that the rate gets worse. But if you're ready to look at a smaller class with higher regularity, you still improve the rate, okay? All right, so what this result says is there exist algorithms that achieve this rate. Or do you actually implement that? The result doesn't say, but there exist algorithms, and you will never be able to construct algorithms with better rates than this one. Okay. Again, by algorithms, I mean a random algorithm that is going to produce an estimate of your integral. Okay. So that's the story for random algorithms. And for deterministic algorithm, if you look instead at the absolute error, that's the best rate you can get. And you can see this rate is not as good as this one. So that's essentially why people prefer to look at random algorithm relative to deterministic algorithm. You could say it's not fair because we don't look at the same criterion. Here it's an absolute error, here it's a kind of error on average, but still the rate is better, okay? So this paper is in Russian. I don't pretend I read it, but some bright people have translated it and also digested and re-explained the result, including this paper by Eric Novak, 2015, which is very nice. So I recommend you read this first, and you get a better statement of these results in this paper. Okay. Right. So you might just believe me at this stage, but to understand a bit better this kind of result, there's this very nice thing explained in this paper by Eric Novak, which is this. Imagine that you're able to construct an approximation Fn of your function based on n first evaluation, okay? And it's an approximation which is at distance n minus r over s in absolute terms. The rate is not arbitrary. That's the best rate you can achieve for approximation error. It turns out that you have to take this as, we'll accept this statement. If you want to approximate f based on n evaluation of f, the best you can do is this, okay? For dimension s and assuming regularity r. Okay, you can prove that. If you accept this result, here is an unbiased estimate that automatically achieves this optimal rate I told you about. And the proof is direct. If you look at this expression, essentially it's you're going to approximate the integral of f minus fn. Okay, so here is just a basic Monte Carlo estimate of the integral of f minus fn. Okay, and then you add the exact integral of fn, and that's your estimate. So based on this, you can see that it's still unbiased. But then if you look at the variance, so this is a constant, the variance is going to be 1 over n squared, the sum of the variances. And because f minus fn is at most this quantity, then this quantity will be the square of this. So in the end, you will get 1 over n squared times n times the square of this. So you get this. Okay? So this is funny because I told you this will be nothing about quasi-Monte Carlo. And here, this improved estimator just use standard basic ID numbers. But the reason why you get from this much better rate is this function fn. And if you're a bit familiar with Monte Carlo, you could call fn a control variate. So it's like if you have a very, very good control variate, you can get even better rates. And this slide essentially is a summary of one part of the proof of Baklavov. He showed that he showed this, and based on this, he showed that you can get this optimal rate using this. Okay, so if you have an algorithm for doing that, you could do that. So it's an interesting insight. I like it again because you realize this time is, I mean, often in quasi or randomized quasi Monte Carlo, what is important is to properly choose location for the points. It's a different story. It's trying to find a very good approximation of fn. You don't really need this insight to understand what's going next, but still I find it's very nice. So I wanted to take the time to explain this. And you could also stop my talk right now and say, this guy is going to do that for a certain fn, which will be a piecewise polynomial. And that's the gist of what we are doing, essentially. But we realize that later, actually. So that's what, it's mature, we realize this, but we, after some time. Because what we are going to do, so this is a square, okay? We're in dimension 2. And you can see I split the square into 5 by 5 cells, smaller squares, okay? More generally, in dimension S, I'm going to split the cube into k power s smaller cubes. I should say hypercubes. And I'm going to simulate points inside each cell, okay, each cube. In this particular plot, again, I'm in dimension 2. I take 5 by 5, and you see there are 2 points in each cell. More generally, there will be L points in each cell, and L will be like tuning parameter of the algorithm, or it will be we'll propose different algorithms based on different values of L. So keep this picture in mind for the rest of the talk. And we are going to call CK the set of the centers of these hypercubes, all right? So the number of evaluation is going to be L times K power of S, So remember in return that K is like n power 1 over S, all right? And again, one way to understand what we're going to do would be to do this stratification and just define Fn to be piecewise constant, piecewise linear, maybe piecewise polynomial. That could be a way to go, but we are not going to do that exactly. So going back to this idea for stratification, in the 60s, Haber had two very nice papers, which were the first estimate that reached these optimal rates for R equal 1 and R equal 2. Okay, because the result of Baclafoff was they exist algorithms, but he did not explain really how to construct such algorithms. So this is I think in history, the first such construction, and it's very simple. Again, you observe an average of n evaluation, but this time n is k power of s, as I just explained. And here the evaluation is that C plus UC. C is one center of all these smaller cubes. And so BK of C is one such cube at center C. And UC, if you take C plus UC, it will be uniformly distributed inside the cube, okay? Because you can see UC for each component, it's between -1 to k and 1 to k power of S, okay? So if I add C to all the components, I will be uniformly distributed like this or like this. So in Haber's first estimate, you have a single point inside each smaller cube, subcube. And again, if you're ready to assume that F is C1, it's easy to check that this quantity has a proper expectation because each term is going to have this expectation. Okay, it's an integral of F over the BK of C, my subcube. Okay, and the variance, again, you're going to take the variance will be 1 over n squared, the sum of the variance of each term, and the variance of this guy, because if you take 2 points inside the same small cube, you will have this kind of Lipschitz property, because again, the f is differentiable and its derivative is bounded. So fu minus fv will be bounded by the derivative times the distance between the two. But these two guys, they are in the same cube, so their distance is at most 1 over k. So because of this, you get this root mean square, or again, it will be 1 over n squared times n's, so 1 over n, times 1 over k, but k is n power 1 over s. So you get this rate in the end. So this is a working approach, but again, it's specific to R equal 1. Okay, so we have an optimal algorithm for C1 function. And it's very easy to implement actually in practice. And again, it's Mathieu knew about this paper or discovered it recently, but I didn't know about it. It's kind of, and we try to get in touch with Seymour Haber, but nobody knows what happened with him. So if anyone knows, I'd be interested. I think he is some probability he's still alive, but I don't think he's still active. I mean, I didn't say as the joke, sorry. Sorry, maybe that's funny. But anyway, we wanted to get in touch with him because we thought he would be very happy we kind of continue this work. But anyway, if you have any insight where he is now, if he's still around. Anyway, so again, if you go back to my connection with this function approximation thing, you could understand Haber's estimate as a bit like that. Like I take Fn to be piecewise constant. And so in each cell, in cell with center C, I take Fn of x to be f of c, and you'll get a different estimator, but with the same properties. But here it's a bit different because we force, we really do stratification. We force that there's exactly one evaluation, in no more, no less, in each cell. But this stratification does not change the rate. What changes the rate is I mean, essentially because you have this kind of approximation, so to speak. This is, yeah, that's what I said. Okay, so Haber's second estimate. This time you're going to use 2 evaluations inside each cell, and you're going to compute an average, but this time of GC of UC, which is an average of FC plus U and FC minus U. So it's a bit like a local antithetical variable, right? C plus U, if U is randomly distributed like that, or C minus U will have the same distribution, uniform inside the cube, okay? But the fact you take them like that, there will be this antithetical effect, which can be understood by just doing a Taylor expansion. If I Taylor expand GC of U, okay, the around C, the first term will be 0, because if you differentiate that, it will be U something plus minus U something, the first derivative. So this function is symmetric and the first term is 0. So then the error is already of order 2. And because of that, you win 1 order of convergence. So you get -1/2 minus 2 over S. But you need to assume F is C2. Otherwise, you could not Taylor expand this function up to order 2. Okay. So you see this idea of Taylor expansion that appears, and you see we're again doing stratification, but this time we have 2 evaluations inside each cell. Okay. Right, so we are going to, again, we started working on this without realizing that some estimates like this already existed. It's Mathieu who found them, but I didn't. And so we developed these more general estimators, but they actually generalize those 2 estimators that I just described. And the way we are going this generalization, we have 2 approaches. First approach is that on trying to do again this cancellation, but on a higher order. So this time, instead of 2 points, maybe use 3, 4, etc. points. And second idea, using control variates based on numerical derivatives. Okay, so the first idea would be specific to vanishing function, but I will explain that in a minute. Okay, so again, I take a function f. I look at this symmetrized version where I take fc plus u plus fc minus u over 2. Again, C being the center of a small cell. And I do this Taylor expansion and up to order 4. The terms of order 1 and 3 are 0, again, because of the symmetry. So there's this term of order 2. And I would like to get rid of it. So I'm a basic guy. When I want to get rid of terms, I just do this kind of development. I take GC of lambda u minus lambda square GC of u. And you will see that these guys will be, give you lambda square minus lambda square, so it will be 0. So the term of order 2 has disappeared. And now your Taylor expansion is, this is this into order 4, okay? So it looks like you could use ideas like that. Maybe you want to redivide everything by 1 minus lambda square. Okay, just a small problem is that if I take lambda to be something else than 1 or minus 1, C plus UC will not be uniformly distributed within your cube anymore. It will be distributed in a bigger cube or in a smaller cube, okay? So that's kind of a mess. And you multiply the volume of the support of C plus lambda UC by this factor, okay? So we are going to solve this problem like this. First, to make our life simpler, we are going to focus on functions that are vanishing. This means that you can define f bar, which is equal to f inside 0, 1 power s, and which is 0 otherwise. So that means that at the boundary, it's already 0, and it reaches 0 in a way that makes it still continuously differentiable, etc. Okay, so not any function is vanishing, of course, right? But for a function like that, let's assume so you can get outside of a cube, but then in the value is 0. Okay, and then what I'm going to take is a lambda to be in absolute value 3, 5, 7, etc. So of course, when I take, for instance, lambda equal 3, I multiply the volume by 3 power s. But this extended cube is now an union of the previous cube. Okay, if you take there's no board, right? If you take in dimension 2, if I take a square and multiply by 3 the length, then I will obtain 9 squares. Okay. So then, if I realize that, maybe I can try to play with this to try to cancel. So if I take lambda equal 3, and I will get again a sum of all the cubes, initial cubes. It's just that I will visit each cube maybe 3 power d times. Okay. And when I get at the boundary, there's a little problem, like a boundary effect, because I need to get out of the cube, but since the function is 0, it won't be a problem. Okay. So basically what I'm saying is that no, if I take the special values of lambda, this quantity will be unbiased, providing I sum over all the initial cubes plus a few others outside of the cube. And then I'm going to combine terms like that so that I get this kind of cancellation like this. Okay. So that's the first idea we had. Yes. So in the end, the estimator looks a bit complicated, but you can see you still you have R terms. Each term you have a certain value of lambda I, and then is it 0, 1, 0? Okay. So you have R terms with R different values of lambda I. The lambda i's will be 1, -1, 3, -3, 5, -5. Okay. And this coefficient gamma I here, they are chosen so that when you do your Taylor expansion, you get FC plus 0, 0, 0 until the term of order R. Okay. So believe me, it's easy to find coefficient like that. It's just a linear system you need to solve. It's called the Vandermonde system. So you find coefficient like that. And I mean, for each term, you had a non-biased estimate. But when you combine them, you have this very low error. And they cancel out until order R. And because of that, you get this root mean square error. Okay. So that was nice, but that was restricted to vanishing function. And then we managed to find, which is already interesting, I'm going to explain in a minute, but we like to treat all possible functions. So vanishing functions are still interesting for you guys if you're interested in importance sampling, for instance, or in Bayesian statistics, and you would consider doing importance sampling. Say, for instance, you want to compute this integral with respect to R power S. Could be the marginal likelihood in statistics, okay? And you say, oh, I'm going to do importance sampling with proposal Q, okay? And your proposal Q could be a Gaussian, for instance, but you're going to possibly simulate your Gaussian using S uniform numbers, okay? And so you have some transformation T of U that transform a vector of uniforms into a Gaussian distribution. When you do that, you obtain a certain function here, which is typically vanishing. Okay, you can check. One of the conditions is that you need your proposal to have heavier tails than the target. As soon as you have that, you get a vanishing function. So I will show you a numerical experiment for the vanishing function, and that will be related to the computation of the marginal likelihood in Bayesian statistics. And we just do that. We do importance sampling, and then you have a vanishing function. Okay, I still have 10, 15 minutes. 10, it should be good. Should be okay. 10-ish. Okay, so second idea, second estimator. Right, so imagine I have a Monte Carlo estimator, which is like that, an average of random variable. The control variate ID is like this. Like you say, I know ZI, which is related to the simulation of the Y, such that the expectation is 0, and which is strongly correlated than Y. In that case, I'm going to replace this guy by this guy. They have the same expectation because Zi has expectation 0. And because you remove Zi and Zi has a strong correlation, this will have a lower variance. Okay, that's a very quick, basic summary of control variance. But essentially, that's what we do. Of course, people might complain at this point, but usually you introduce a coefficient beta and you try to find the optimal beta. But let's say I'm lucky, I know I can take beta to be 1. So I could do something like that. So in our case, again, if you look back to Haber's second estimator, I had an average of GCUC where GCUC was this function. And I could Taylor expand it and only the terms of order 2, 4, 6, even terms will appear. I always forget odd and even numbers in English. So I say 2, 4, 6, and 1, 3, 5. So, okay, so this guy is bothering you in the sense that it will be the leading term that will in the variance. So I want to get rid of it. So easy, I'm just going to remove it. And I take this function minus this minus its expectation. So if I remove the expectation, it has expectation 0. And is it going to be strongly correlated with GC of UC? Well, yes, because it is the leading term anyway. So that looks like a obvious idea. Computing the expectation is not a big deal. The problem with this is that you will need to compute variation. So at this stage, there's some small disagreement between Matthew and I. Myself, I think that it would be interesting to use that directly because these days there are very efficient tools using AutoDiff that compute derivatives for you. So you could actually compute the exact derivative and get an estimate and you will be done. That would be great. But then Matthew's point of view is a bit formal. He says, no, we're saying we do quadrature, and quadrature is the problem of approximating integrals based on evaluation of f. So if you use evaluation of derivative, it's a bit like cheating. So anyway. And also his point, another point he's making that you can't say anymore that what we're doing is optimal because this optimality result is for this problem and not another problem. So anyway, we have not explored that, but you could use as a control variate, for instance, this, and it will require variation. What we're going to do is we're going to use numerical derivatives. So numerical derivatives, I'm sure you're all familiar. It's a very hot topic. This is 600 or more pages on numerical mathematics. How many pages you think there are on numerical derivatives in this book? I promise you 0. It's like the most boring subject in mathematics, apparently. Nobody wants to talk about it. The Wikipedia page is, from time to time, there are some people who make changes that are wrong. It's a bit of a mess. Like people say, oh, it's kind of obvious. It's boring. Anyway. So we're going to do that. And sadly, we had to reestablish things because nobody takes the time. I mean, for dimension 1, you have formula. And then for multivariate problem, people say, oh, figure it out. It's left as an exercise to the reader, something else. Okay. So anyway, in case you don't know, this is the most basic formula for approximating the first derivative for a function f. You take some small number h and you do this. Again, it's based on Taylor expansion, you can figure out, and you give you the first derivative plus an error of order h squared. Okay. In this stage, you say, this is silly. I want the exact derivative, so I'm going to take h to be super small, like 10 minus 35. The problem with that is that this formula, they are ill-defined, which means that when h becomes too small, then you have you're going to subtract this number to this number. They are super close. So the numerical error is going to be quite big relatively, actually. So actually, what you want to do is to take h not too small. And that's a motivation to look at a higher order formula like this one. So this one, you have more terms. And you, 5 minutes, yeah. And you still approximate the derivative, but order 4. It's not really you want it more accurately, is that it lets you take h a bit larger, essentially. Okay, and you can find a lot of formula like that at any order. for any derivative, etc., etc. But again, if you look at the literature and the subject, as soon as you look at multivariate derivative, it's not really clear because nobody takes the time to do the theory or even write the formula. So what we did was very funny. I found this Python package developed by physicists who were computing numerical derivatives at any order and any dimension, and it was super fast. I could not understand what we were doing. So in the end, I looked at the code, and as always in physics, these guys are very bright, but they never explain anything. So I figured out what they were doing, and that's super smart. And it's really a shame that nobody explained it, because in a way, if you think about it, if like in our case, you want numerical derivatives on a grid. Our grid is the set of the center C, in the stratification, the center of the cubes. And we want to approximate all these derivatives at all the C's. So it's like a grid. And if you want to approximate quickly all these derivatives, you can evaluate F at all the centers, and you can do some linear combination on the terms to get all these derivatives together. And this is based on the fact that if you look, just 1 minute, if you look at this one, it looks like you need to approximate the derivative at x, you need x plus h and x minus h. So if you're in a grid, in a certain position, you just need your friends from top, bottom, left, and right, and you combine in a certain way, and you get all these numerical derivatives. And that's what we do, and you can do that at any order, etc. And you get numerical derivatives that are not so accurate, but we did the math, and we managed to make just so that the error is small enough so that you don't perturbate the error rate we want to obtain in the end. Okay, so we compute FC at each C. We combine them in a certain way using the package by very bright people and different orders. And in the end, we just, so I'm a bit late, and we do this. So it looks a bit horrible, but it just, if you don't add this term, it was just a Bers estimate of order 2. And this is our control variate. This d hat is an estimate of numerical derivatives. And if without the hat, you would just have these quantities of expectation 0 that cancel the first terms if your Taylor expansion. Anyway, and the funny thing is that the number of evaluation in each cell is now free, actually. I could explain later. Anyway, so I'm a bit late. So we can prove that this one works for any function f in your CR class. You get the optimal rate. We also had this error, which is true with probability 1. And the error is even 0 if f will be a polynomial. Anyway, so I have mainly 2 minutes left for numerical result, 2 minutes. So that's a non-vanishing function. So that's the second estimate, dimension 1, 2. That's Haber's estimate. So it's like our estimate of order 1, 2, 4, 6, 8, 10. Do you see why we cut here? It's just because this is like a relative mean square error. So we divide by, so it's the mean square error divided by the true quantity square. And where below this line, you're below machine epsilon. So you get a non-biased estimate, but each replication is exactly the same because the variance is lower than numerical error. That's the first time it happens in my career. I have such a low Monte Carlo variance. I could not believe it. So you had to truncate it. And you see order 10, it goes to 6, 8, 10, it goes to 0 very quickly. So in dimension 1, 2, 4, 6. As expected by the theory, you get a better result when you increase R, but the slopes are not, I mean, the value of the slope is not so high because it's divided by the dimension, okay? And for the vanishing case, we use this Pima Indian data sets toy example, a bit of a joke, and you get again, I mean, by increasing R, you get better and better rates, okay? I should say your estimate depend on R, and here I'm looking at functions that are basically C infinite, okay? So you expect the estimator to get better and better, but it is asymptotic rate. So here in this case, for instance, you see if I take the number of evaluation too small, then maybe a smaller value of R do better. Anyway, so that's 6, 8. So we managed to make it work reasonably well until dimension 8 or 10. So to conclude, I think I'm good. So these optimality results were known for a long time, but a bit forgotten. And we managed to propose practical estimators. You could also estimate the variance from a single run or small number of runs. We have a method for that, but it's in the paper. I don't have the time. You'll not use these methods really, to be honest, when dimension is 100 or 200, because they are optimal, but the improvement you get of the Monte Carlo is so small, it doesn't matter anymore. There is this randomized quasi-Monte Carlo strategy of R2N you could use instead, which is like typically working well, whatever the dimension, okay? But for smaller dimension, what we do is optimal. I mean, there's no way you can do better, at least asymptotically. That's what the Baklava says, I believe. Thank you very much.
I'll do the running.
Hi, very nice talk, thank you. I have many questions actually, but I'll ask just two. The first result about the RMSE, where you have the extra term R over S and to the minus over, is this true for LP? So because this is MSE, right? Is this true for LP bound? Can it be proved, something like this?
Good question, I don't know.
The second, yes, okay. The second question is, does this apply to self-normalized importance sampling?
I need to take a pen of paper, not immediately.
Okay, yeah, sure.
I can actually answer the first question if you want. I think there's this field called information-based complexity where they derive all these optimal rates. So I think there is bounds also for other P's than 2.
Yeah, and there are also results on not looking at this criterion, but looking at like you want your error to be smaller than epsilon with this amount with this probability.
I mean, you kind of took away my question at the end with your last comment, but I was gonna ask exactly with growing S. I mean, because you have integers K, so I mean you have like the asymptotic only kicks in at 2 to the S, I guess. So you can't do it less than those points. Is that right? Yeah. Anyway, but. So what I'm trying to say is like it really is a method for intermediate dimension and not for really high dimension.
In Finland, I did talk again, and someone said, what if you have a function in a large dimension, but the net of effective dimension is smaller?
Yeah. Okay, that was my next question. Anisotropic. I mean, to be fair to the QMC community, I mean, what people do there is that you care about really what happens when S gets very large, and when the dependence on the dimensions is like anisotropic, like one variable is more important than others. So I think that's important. But my other more mathematical question was regarding, sorry.
One more comment about that. The only idea we have at the moment is to say, so we're stratifying the cube by splitting K times in each dimension. You could imagine that some dimension you split less and others more.
Yeah.
And I'm trying to think of ways of doing that a bit automatically. See if you have any insight about that.
A more mathematical question was with your derivatives at the end. What do you do at the boundary? I mean, the big problem with derivatives, numerical derivatives, is always at the boundary. Because the points h minus 2, minus 2h, minus 3h are not in your domain anymore.
No. It's when you're close to the boundary, instead of using your friends from around, you use your friend that's inside. You don't try to go outside.
Yeah, but that slows it down, and the algorithm gets much slower because it's not as simple.
We're assuming that the function is CR of a 0, 1 closed. Okay, so it's still regular when you're
Let's see.
It's a function, but still continuous at one. And if this function would be going to infinity, then it would be a different problem. And
Okay, great. Well, thank you very much. We'll stop the questions now, but I'm sure Nicolas will be happy to have more questions at the break. Yeah, thanks again, Nicolas.
thank you.
So our next speaker is Omar Ghattas. So we've had to do a little bit of change in the calendar again, due to one speaker being stuck on the train. So Christophe is going to arrive, but he'll be there a bit later this afternoon. And so Omar has very kindly agreed to swap his talk with Christophe. So Omar Ghattas is a professor at UT Austin. I was going to read out the various professor titles, but they might be a bit long, so I might just leave it to you, Omar. And I should get this.
Yeah, this doesn't, the clip doesn't seem to be.
All right.
Is that, is the spring broken or am I just
No,
not doing
it
it
does
right?
look broken. Yeah. Okay.
But this is fine. I can.
You can use this if you prefer.
Ah, excellent. Thank you. Okay, well, it's a real pleasure to be here. And I'm sorry I missed yesterday's festivities. I arrived late yesterday afternoon. I had to teach class Monday morning. We were talking about digital twins. So it's relevant. And it's an inverse problems class. Anyway, so I can just do this over the Wi-Fi, right? I don't have to plug in anything.
Yeah, you just join the Zoom and
Okay.
share.
Just share. All right. So bear with me for a moment here. Start the broadcast. 3, 2, 1. And is that it? Okay. So I just have to get the. So that's not what's on my. There we go. All right, and then rid of this. All right, so I just need to put that some. There it is. Okay, is that okay? All right. So what I'd like to talk about are neural surrogates, neural networks as surrogates for parameter to output maps. These could be parameter observable maps in the context of the Bayesian inverse problem. This could be parameter to some utility function which measures the utility of placing sensors or otherwise designing the acquisition system in optimal experimental design, or ultimately in a decision-making problem, the output would be an objective function, a control function of interest, or some risk measure associated with that. So all of these, if the forward problem is expensive PDE, if the parameter space is high dimensional, these will essentially be intractable without some form of approximation, some form of surrogate for the parameters output map. And the idea is to investigate neural networks, and in particular, neural networks that to some extent, in some sense, try to learn the geometry of parameter space. This is joint work with Lianghao Cao, who's the error estimator work is his, Peng Chen, who's involved in many of the aspects, DC Luo, who's working on the optimal control under uncertainty, Tinsley Oden, who was involved in everything, Tom O'Leary Roseberry, similarly, his PhD dissertation was on the original work on these neural surrogates that sort of understand the low dimensional mappings between inputs and outputs using sensitivity information. Simone Puel, who is using these ideas to try to understand and invert for the slip on subduction zones, major subduction zones in particular. He's working on Japan right now. Umberto Villa, involved in many aspects, including software, and Kei Wu, who worked on optimal experimental design. Okay. So there's a number of sections here. I probably won't get to the last one or two, but let's see how far we go. The motivations, this is a workshop on digital twins. And so what we understand as a digital twin, what I understand as a digital twin is there's a physical system and there's its digital twin. There is a flow of information from the physical system to the digital twin. That's a data assimilation problem or an inverse problem. So one has, instrumented the physical system, sensors, satellites, strain gauges, etc. And you'd like to update your knowledge of the physical system by solving an inverse problem. There is a flow of information in the opposite direction. Now we have this updated model with reduced uncertainties if we've done this in a statistical inference framework. So now we would like to use this updated model to control the physical system. And this can be in some evolving sense. All right, so the fundamental problems are data simulation and some kind of optimal decision-making, optimal control, optimal design, or even optimal experimental design. We could be steering the sensors, optimizing the data acquisition to further reduce our uncertainties in the model itself. So I've listed there a number of challenges, but you probably cannot see them. The font is quite small. I can barely see them from here. But what I'm going to focus on, so I mean, issues with real-time data simulation, real-time optimal control under uncertainty. You're going to build these digital twins for critical systems. I've shown some examples here. I'll talk more about this one, the subduction zone dynamics, ice sheet flow in the polar regions. Antarctica is pictured here. This is a problem of drought in the Western US, not so much in California anymore, but the West has been plagued the US has been plagued by droughts over the last several decades. So this is using satellite information. This is interferometric synthetic aperture radar to infer the vertical displacement of the Earth, which is an indicator of how you are extracting water from an aquifer. And as you do that, you have subsidence. So use that signal from space, solve the pore elasticity problem, so coupled mechanics and flow and porous flow, to recover aquifer properties and use that to plan your future extraction and pumping of water in order to manage the water resources in a drought-stricken area. So that's another digital twin example. Here's a flow control problem. This is a shape optimization on the left. So this is a Navier-Stokes with a Reynolds average, RANS model, optimizing the shape of a wing sections. This is a design problem, but the control problem is, you can see here a blunt body with some flow, and you can see some secondary flows behind it. And the idea in this problem is to control the injection or suction of fluid on the surface of this blunt body to essentially minimize the viscous dissipation in the fluid and to eliminate these secondary flows and to allow the flow to be attached. So there's there's sensing, there's an optimal control. This problem has uncertainty in the inflow, and so it's an optimal control under uncertainty. Here's a manufacturing problem. This is a block copolymer. So it's essentially a non-local Cahn-Hilliard equation. So it's a Cahn-Hilliard with a non-local operator that represents a melt of two polymers that form nanostructures. And I really don't think, oh, okay, I can do this. All right, I should have done that from the beginning, shouldn't I have? All right, so you have some target morphology that you'd like to construct. So these are nanoscale. So we cannot form structures of a few nanometers, but we can create block copolymers that will form these nanostructures through a self-assembly process. They need some guidance. So the idea is to apply a laser and to use a heat source to encourage them to form certain structures. So this might be initial structure, and we might have a model, and we have ultimately a target morphology. And so by controlling the laser in an appropriate way, we can get them to form, they can form strips, they can form different patterns, and these might be useful for nanoelectronics. And this is the idea. But the model itself isn't perfect. So the usual data assimilation framework, in this case, you can do X-ray scattering, reflects off the nanoscale morphology, forms images that you can use then to invert for the actual structure that you have, update your model. In this case, this would be state estimation, and then control the whole process, and it would repeat. And this is on the order of seconds to minutes is the time that you need to react. And so you need surrogates. So the argument I'm making for all of these, and I'll say more about this one, the Antarctic one, also you're trying to estimate the friction at the base of the ice sheet. You have surface velocities that you get from synthetic aperture radar, and you have to go backwards then solve an inverse problem to estimate this friction at the base of the ice sheet, because the ice is either frozen in some places and you have essentially no slip condition, or it's freely flowing due to lubrication, so there's fluid underneath the ice sheet. In other regions, so you have a free slip boundary condition, and most places you have something in between. So this map shows the solution of the inverse problem. This is the mean of a Bayesian solution, which is showing you in red the regions where there's little resistance to the sliding of the ice sheet. So if there were a collapse of one of these ice shelves, so the ice shelf is the floating part in the Ross Sea, for example, here, there would be little to keep this ice from flowing into the ocean, because that ice shelf is buttressing the flow of ice from land. And so this is a concern. So you'd like to use satellite data to update. Now, this is a longer time scale, but you'd like to use these passes every few weeks of the INSAR satellites to update your knowledge of the ice sheet itself. On shorter time scales, you may try to have interaction with the ocean and try to understand how the ocean is affecting the ice shelf, which then couples back to the ice sheet. Okay, so in all of these, one of the challenges, which we'll focus on here, is how do you construct a surrogate which maps from the parameters of the inversion. If you're doing data assimilation, it would be the state. If you're doing a classical parameter inverse problem, then it's a set of parameters that themselves may even be dynamic. Map those to the outputs of interest, which in the context of the inverse problem is a data misfit. In the context of a control problem is something like the distance from a desired morphology. And it's frozen. Okay. Let's see. There we go. Okay, so maybe that unfroze it. No. Okay, so I got a little bit too smart for myself. Why is this happening? Oh, there we go. Okay, I don't know why. All right, so we're trying to learn this mapping from parameters or state or the control variables, or all three of them, to quantities of interest such as data misfit or a control function like that dissipation rate, viscous dissipation rate in the fluid flow problem, or an optimal experimental design, some utilities such as the expected information gain in placing sensors. Okay, so that's the challenge here. There are many other challenges: real time, uncertainty, doing everything under uncertainty, the challenges in data assimilation and optimal control under uncertainty in general. But we're focusing on the surrogate. So here's a problem that we're working on. And this is the Japan trench over here. It's a major subduction zone. The Pacific plate here is subducting underneath one of the smaller plates, which is left over from the North American plate, but it's a plate that contains Japan. And so the Pacific plate, which is denser and thinner, is being pushed underneath the continental plate. And the two plates are stuck. Friction is holding them in place. Or so we thought. In 2011, the accumulating strain was so great that the massive rupture occurred, the Tehuka earthquake, magnitude 9 earthquake, which unleashed 20-meter tsunami waves, which inundated the coast of Japan, and in particular damaged 3 reactors in Fukushima. It also sent seismic waves propagating through and destroying buildings in Tokyo and other cities. The Japanese were very well prepared for the seismic waves, but they were unprepared for the tsunami. It was thought that those plates were locked, at least in the central region, that they were locked, and there would be, that essentially that zone, certainly in Japanese recorded history, had not produced a major rupture. And it turns out it did. And well, the result was 18,000, 19,000 dead or missing, and $400 billion in damage. So the idea is, if you look at these yellow triangles here, these are locations of GPS stations, which are recording motion displacements. And there are even some offshore stations here, which essentially record the hydrostatic pressure. So that gives you essentially the depth. So you can tell if there is an increase in wave height. These are time dependent. And there are plans to further instrument the zone and connect it with fiber optics, for example, to collect dynamic information of the pressure, which then you would invert for in real time to infer the motion of the seafloor. So it's this vertical motion of the seafloor which lifts up the water column. So as the plates are subducting and you get slip, the overriding plate pushes up the column of water. When the friction is overcome and you get the slip, the overriding plate pushes up a column of water, and that creates gravity waves, which then propagate along the surface, and that's a tsunami. So the idea is to try to predict all of that. These inversions here are static. We also have another code branch that's doing the dynamic inversion. So far, that's in 2D and it's being extended to 3D. But these are 3D inversions using these stations, the displacements in these stations to invert for coseismic slip. So there's, in fact, yeah, we have a picture here. So these are the GPS stations, and this is the slip on the fault zone. This is the 2011 earthquake. And so this is how, this is the actual rupture. You see the hypocenter there, the green star, and then you see the magnitude of slip, 40 meters of slip. It's quite a bit of slip on the fault. And that's greatest in this region. This was assuming known Earth properties, assuming we know the elastic properties of the Earth, and inverting just for the slip on the fault, which is a dislocation, it's a discontinuity in the displacement. And these are the remaining data misfits. So they're not quite zero, they're in the order of centimeters. And that's because we've been taking as given an Earth model, and instead what we need to do is jointly invert for both the slip and the Earth model. It turns out the Earth model is not accurate, and we can use this earthquake data to try to improve the accuracy. So there will be a joint inversion. In fact, in 2D, we've done joint inversions. All right, so let's talk about surrogates and the difficulty in constructing them. So clearly they can help accelerate Bayesian inversion, optimal experimental design, optimal control. These are the ingredients of what I view of digital twins. But as we just saw in Nicolas's previous talk, there's a curse of dimensionality. You saw this expression, maybe with different definition of the parameters. But if you have exponentially deteriorating convergence rate of approximating a function with n samples in dimension d, if you have smoothness, you can make up for it. But you ultimately have this curse of dimensionality, and many available surrogate methods suffer from the curse of dimensionality. The question is and that was the question at the end, if you have a high dimensional problem with an effective dimension that's much lower. If the inputs affect the outputs in lower dimensions, can we exploit that? Many problems in science and engineering have intrinsic low dimensional structure. Parabolic problems, the dimension decays. The dimension is exponentially. There's an exponential decay in the effective dimension as you increase, the intrinsic or ambient dimension. There is essentially the singular values of the Jacobian of the parameter observable map decay exponentially. For elliptic problems, it's algebraically. Hyperbolic problems, it depends. That's a challenge. We'll talk about that at the end. In principle, you can construct model hyperbolic problems that have no decay, where the singular values are all one. But those are model problems like a transport of a wave that, you observe this wave and there's no loss of information. In most hyperbolic problems, waves propagating have a loss of information through attenuation in the medium, through reflection and scattering off of interfaces. So there is some loss of information, but the effective dimension can be higher, and that's a challenge. Okay, so what we have here is some notation. We have model parameters M with an associated probability distribution nu. There are outputs Q that could be the observations at particular instrument locations, or it could be a scalar output as in a control problem. You have an objective function and state variables U. So we have a parameter to output map, which Q depends on the model parameters through the state U. And that dependence is dictated by the forward problem, which I'm indicating here as R of u comma m equals 0. Often parameter space is infinite dimensional. For example, initial or boundary conditions, source terms, if you've got heterogeneous coefficient like that subduction zone inverse problem, or even the shape. And so we need surrogates that can handle high dimensional inputs M, and it could be that the outputs are high dimensional. Also, you saw in the Japan subduction zone case, all those triangles represent observations of the displacement, three components of displacement on the surface of the Japan land area, and some limited offshore information as well. So Q could be high dimensional itself. Often it's finite dimensional, although in the satellite cases, we have an INSAR image that's effectively infinite dimensional. And there you have grid spacing of 5 meters or 10 meters when the physics is resolved in Antarctica, for example, on elements of order 1 kilometer, maybe half a kilometer at the finest. So there are some theoretical dimension-independent convergence rates for certain kinds of neural networks, and that's inspiration to try to construct neural network surrogates that exploit this intrinsic low-dimensional structure of the map. So how is that? How do we discover that structure? Well, the idea is very simple. We first compute a spectral decomposition of the expected Gauss-Newton-Hessian. So this is the Jacobian of the parameter to observable map or parameter to output map. So the Jacobian transpose Jacobian. You then sample it, it's expectation. So we're going to replace it with a Monte Carlo approximation, sample it over parameters space, drawing samples from the probability distribution for M. And then we're going to construct the spectral decomposition. I'll say a word in a second about the cost of doing this. This is incredibly expensive, but it turns out using adjoint methods and various tricks, randomized SVD, this can be done relatively efficiently. We'll say more about that. That's on the input space. So this is the dominant eigenvectors form a basis for reducing parameter space. And the coordinates of that basis then are the input into the neural network. So we don't try to build a neural network from high dimensions to high dimensions. Of course, that's crazy. You will have huge number of weights, which means you need a large amount of training data. Training data means solving the forward PDE many times. So that's out of the question. Instead, we're going to essentially construct this low dimensional representation. And then the same thing on the output side. The output side, you can take what I call the data space Gauss-Newton-Hessian, or the inside out Gauss-Newton-Hessian. So it's Jacobian transpose that lives in the data space, and you compute the expectation of that and then find a spectral decomposition. Something else you can do is just POD, which is the output transpose. That's cheaper. It doesn't require sensitivity information. And actually the data space Gauss-Newton-Hessian is a first order approximation of the POD. And that creates an output basis. And again, it's the coordinates of that output basis that dictate the neural network is going to live in those low dimensions. And so then you fit a neural network. We like ResNets, in particular, if you're using these two, the Gauss-Newton-Hessian, the dimension will be the same, and you can build a nonlinear ResNet, and that provides a further reduction. Notice these tall, thin matrices here. So sigma is the activation function, and so there's a further dimension reduction that's involved, and that's a nonlinear neural network type dimension reduction. Now you might ask, well, why not use an encoder decoder? So just put in a bunch of weights here and let the neural network figure out the low dimensions. So I have some numerical results to compare with this approach. And as you can expect, you're going to have a large number of weights. If you just open this up to the neural network, throw in all those weights, millions of weights, right? This input dimension is millions. So you're going to have a huge number of weights here, and it's going to take a large amount of training data. Now that is a fully nonlinear representation, but it comes at a price of having the neural network with the associated training, and the training it's a highly non-convex problem. So trying to detect that and find it is going to require a large amount of training data. Instead, this uses our knowledge of the sensitivity of the input-output map, accelerated through randomized algorithms and through adjoint-based computations to figure out those input and output subspaces. Okay, so a word about the speed with which we can do this. Maybe I'll skip this since time could be an issue. So the basic idea is you never form these operators, you just form their actions on vectors using randomized SVD, and then each action of a Gauss-Newton-Hessian on a vector amounts to one linearized forward problem, one linearized adjoint problem. but they all have the same coefficient matrix. So of course, if you're using direct solvers, the cost is so the overall cost is number of Monte Carlo samples multiplied by the effective rank of these Gauss-Newton Hessian of the composite Gauss-Newton Hessian. And there's 4 simply because there are 2 at every matrix vector product, and it's randomized SVD using, this is a double pass algorithm. So anyway, it scales the number of Monte Carlo samples in parameter space and the effective rank. But the effective rank, they all have the same operator. So if you're using a direct solver, it comes for free, you factor once. If you're using an iterative solver, it tells you should invest in an expensive preconditioner that can be amortized over these R matrix vector products. That's basically all I'll say here. Finally, in the end, the effective rank is related to the expected information gain. The eigenvalues of this J transpose J, this Gauss-Newton Hessian, the expected information gain is related to the log of 1 plus these eigenvalues. So if the eigenvalues decay rapidly, then you can truncate early. You don't need many matrix vector products. That tells you the problem has effective low dimensionality. Okay, I'll skip this Antarctica example in the interest of time. Okay, so what can you say about the accuracy of this approximation? So now, assuming that the low dimensional map is represented exactly, so the only approximation is in the input subspace and output subspace reduction, the expected error is bounded by, this looks like the typical SVD result. So it's bounded by the trailing eigenvalues of both the Gauss-Newton Hessian, and in this case, this analysis is for the POD on the output space. So where you truncate the spectral decompositions, both on the input and the output, that dictates the remaining error. So if the eigenvalues decay rapidly, then you have an accurate approximation. And now when you add the fact that you have a neural network in between, well, that adds extra neural network error. So there is, of course, just the Monte Carlo error in training the network, the empirical risk minimization. You're going to have a certain amount of training data. So there's error associated with that. And then there's the error associated with the neural network representation, because as we all know, universal approximation theorems in practice, they don't, you have to deal with non-convexity. You're going to get a local minimum. There's going to be error there, and you can throw more training data in the hope of getting you something better, but often you're just stuck with 95% accuracy. Or something like that. All right, so here's an example, Helmholtz inverse problem. This one, so we're inverting here the parameter is the log of the wave slowness, not the wave speed, the wave slowness. And we've got a grid with 16,000 parameters. There are 200 observations. And we're going to compare this idea using the Gauss-Newton Hessian to detect a low dimensional subspace, along with a ResNet in that subspace. We're going to compare that with just a fully dense, from 16,000 to 200 mapping, a neural network that's fully dense, an encoder decoder, where we tell it the effective rank. So the effective rank that we discover using Gauss-Newton Hessian, we'll share that information with the encoder decoder, but it's going to have its own reduction on the input and the output, where the weights are just trained by the cost function that's being minimized, and you just try, the neural network just tries to figure it out on its own along with the optimization algorithm, and then we're also going to compare it with using PCA essentially on the input, not the Gauss-Newton Hessian. Okay. That's funny. All right. That's not the case in the PDF on the laptop, but that's fine. What this thing showed you was a sample from. This was a sample from parameter space. It was just a heterogeneous medium. And then this was going to show you these are observation locations on the top. So this represents like a geophysical exploration. You have sensors on top, and then this was supposed to show a wave field, a Helmholtz wave field with reflections off of interfaces and things like that. You're stuck with my artwork. Sorry. Okay, so this shows the accuracy, and if you have a full dense network, so a multi-layer perceptron, you have the green curve here. So this is 86% accuracy, and this is as a function of the training data. So if we increase the training data, how does the accuracy behave? And, it sort of saturates. You never really get above, what is that, about 89%, even when you have large amounts of training data. Whereas this adaptive ResNet using these projection ideas, you already have over 90% accuracy in the low training data regime, and eventually saturates above 92, 93%. The green, the red is truncated dense. That's the encoder decoder. So that's just turning it over to the neural network and let it figure things out. It starts to catch up a bit, but there's still a big gap with the using sensitivity information to detect the subspaces in which the inputs are affecting the outputs, and which the outputs are affected by the inputs. Okay, that's information we have. Why throw it away? This is what happens when you use a PCA for the input reduction. So in other words, you have a prior on the parameters, you have a covariance, you just do, the Kullback, the Karhunen-Loew, 2 KLs. Karhunen-Loew reduction on the input space. So basically this, effectively, if it's a smoothing prior, these are just going to be the smooth modes. But that doesn't know the parameter observable map. It doesn't understand the PDE. It doesn't understand how the parameters are propagated into the outputs. And so it's cheap to do. But what happens is you get a gap there. So this is, quote, the right thing to do, which is to use sensitivity information. And this is the wrong thing to do, which is to use the input. All right. So let's show this for use inside a Bayesian inverse problem, and particularly inside an optimal experimental design problem. So that same Helmholtz problem, we're going to locate the sensors. We're trying to figure out what's the best sensor location in order to give us the most information gain in the solution of the Bayesian inverse problem for wave scattering. Okay, so trying to recover the medium, which is the wave slowness, from observations on the top surface. But where do we place those observers? Where do we place the seismometers? All right, so the usual Bayesian inverse problem setup. I don't think I have to go through this, but data Y, observation operator B, script B, state U, which depends on model parameters M, some noise epsilon. The usual expression for the posterior in terms of the prior, and there's a likelihood that relates the two together, and this is the usual likelihood. So we want to go to the outer problem that's wrapping around the Bayesian inverse problem, which is optimal experimental design. And the optimal, so this is one formulation. It's the maximum, we're trying to maximize expected information gain from between prior and posterior. So this is expectation over the data of the Kullback-Leibler divergence between prior and posterior, where the KL divergence looks like this, log of posterior over prior, expectation of that with respect to the posterior. This leads to if you do this in brute force, this leads to a double loop Monte Carlo. We don't actually do it in this form. There's some transformations you can make, but you end up with one loop computing the evidence, the normalization constant. That's one loop, and then wrapped around another loop is sampling over over a prior. So these embedded loops, this is a problem. It's very expensive, and it leads to bias in that. There's bias in the overall computation, even if you're using Monte Carlo, because the inner loop isn't fully resolved. So the idea is to use these neural network representations of the parameter to observable map, use them as a proxy for the actual PDE-based parameter observable map, and then compute this KL divergence and the expected information gain, and then use that to optimize the sensor locations. Okay, so the basic result is about a factor of 1,000 speed up, taking into account the cost of the construction of the surrogate. So you can't ignore that. You have to count that. But if you do count it, even then, there's still a factor of 1,000. I'll show you some pictures with comparable accuracy. This is a typical result. So the truth is the blue crosses here. This shows you the expected information gain. So this is expected information gain on the vertical axis. The horizontal axis is the number of samples, Monte Carlo samples. So each sample involves a PDE solve if you're doing the ground truth. This is just the outer loop. The inner loop itself has 60,000 samples. We're trying to get the evidence computation to be accurate to reduce the bias in the outer loop calculation. So altogether, this represents about 6 million samples, 6 million PDE solves. Those are the blue crosses. The orange is if you replace the blue with that same neural network that we had for the Helmholtz operator. So that neural network, which maps from the reduced space of parameters to the reduced space of observables using sensitivity information. And then the green is if you do a double loop Monte Carlo, which is restricted to the same number of PDE solves as the neural network. In other words, the neural network required several thousand PDE solves to train. And then if we say, all right, those several thousand PDE solves, that's your computational budget, go use it to do double loop Monte Carlo. And this is what you get. You get a, it's quite far away. I mean, this is very inaccurate. Whereas using those PDE solves to build the surrogate and then using the surrogate to replace the PDE solves in the sampling gives you something which has comparable accuracy. So again, this is about a factor of 3 orders of magnitude. So 6 million PDE solves in the ground truth versus on the order of 3,000 or so for the orange. And what this represents over here is the expected information gain as a function of the number of sensors. Now, we want to, this is a combinatorial problem where you place the sensors. So we can't really solve this exactly. So what we can do is we can try random sensor configurations. I mean, we can't solve it exactly for the expensive PDE and for a large number of sensors. And what we can do is we can generate random samples of the experimental design of the sensor configuration, and that gives you this distribution. So this is a distribution of the expected information gain, and the magenta cross on top is the one that comes out of the optimal solution using the neural network. Using the neural network and then taking that configuration back and computing the exact EIG, exact expected information gain using PDEs. All right, so this is all exact evaluation as opposed to this one here. Okay, so this paper is appearing, and the last thing I want to talk about very quickly is this idea of, okay, so we've trained the network. F is the network, Q is the parameter to output map. So we've trained it in the L2 sense. But if we're going to then take this neural network and deploy it in optimal experimental design, Bayesian inverse problems, and optimal control, using optimization style algorithms, these require derivatives. Just because you've trained the neural network on function value doesn't mean your derivatives are accurate. In fact, they can be terrible. So the idea is to train on derivatives also. But the problem with derivatives is this is the Jacobian of the parameter observable map. This is a high dimensional object. So if you have 16,000 inputs, 200 outputs, this is that size of a matrix. So this is the Frobenius norm. So officially this is what we need to do, but this is crazy. Just to compute the exact Jacobian of the parameter observable map, this is no longer randomized SVD where we can just hit it with some random directions and expect that there's a small number of those random directions that tease out the information. Well, I mean, ultimately we're going to do that, but formally, this would require as many PDE solves as there are parameters or data, whichever is less. So this is problematic. And so what do is we, using this neural network construction that has these projections, then you can show actually that all you have to do, that in order to train on the full Jacobian, effectively, if you have a neural network construction like this, effectively it learns the low dimensional information. So the problem is if you try to learn only in the low dimensions and not say anything about the complementary dimensions in which the parameters don't influence the output. So you expect the Jacobian action in those directions, there should be 0 singular values. The problem is the neural network doesn't know that. And if for an arbitrary neural network, it doesn't know that. It can put junk in those other directions. So despite the fact that the inputs do not affect the outputs, if you don't train the network and tell it that there's 0 information in the complementary directions, you cannot get away with just informing it with the order R informed directions. That's for an arbitrary network. But if you design a network of this type, then it excludes, and so that's this result up here, that says that in the complementary subspaces, the network doesn't do any, in fact, it reproduces 0. So it does exactly the right thing. And then you can do these reductions. And so you need only order R PDE solves and storage to train the network in these low dimensions. Okay, that's the basic idea. And so this is, I'll just show you some results here. This is a large deformation hyperelasticity problem. And what you see is, first of all, training the network with derivative information improves not just the derivatives, we'll see that in a minute, but actually the L2 accuracy as well. Well, you might expect that. So for a given number of samples in parameter space, you're using derivative information at each of these samples, made efficient through adjoint randomized ideas. That improves L2 accuracy. It's more information contained at each sample point. And that's the red curve here. So with a small number, this is what, 64-ish training data, you already have over 90% L2 accuracy. Whereas if you use only L2 training on the function value, it's much lower. Now, eventually it catches up. If you give it enough training data, just L2, it'll catch up. But it's more training data, more PDE solves. The Jacobian, the so-called H1, we're calling it H1, but it's the Jacobian of the parameter observable map. If you compute the Frobenius norm of that, if that's your measure of accuracy, using the H1 training is now, it's not very good, but once you get to some reasonable number of training data, the error in the Jacobian is quite large, whereas if you just use L2, it's very slow to catch up. Okay, then the last minute, I want to talk about optimization under uncertainty. So the same ideas as before. There's a neural network that maps random parameters to the outputs of interest. But what we're going to add here is we're going to add that the network has to map the control variables too, the optimization variables. So there's the random parameters and the optimization variables. We're going to find low dimensional representations of those, build a neural network in the input space, and then the outputs here. In this case, we're actually learning the full state. We don't have to, we could just learn the objective function, but we're learning the full state in order to allow us to use different risk measures. This is optimization under uncertainty. So we could be, the simplest is the mean or mean plus variance, or various other risk measures that are more sensitive to tail probabilities like conditional value at risk and others. So in this case, we're actually just learning the state itself, and the full state, and then we can reuse that in different expressions of the objective function. And so this is just a model problem, and I'll stop with this. So it's flow over a bluff body. There's an input. So the inflow has some randomness. So U infinity is a random variable, has a random prefactor, and so we're uncertain about the inflow. And what we're trying to control. Here's the control function, which is in red. So this is the injection or suction of fluid on the top and bottom surfaces of this bluff body. This is a standard test problem that's used in flow control. And we represent the flow through B-splines. So it's parameterized upper and lower surface. In this case, we're using CVAR as the risk measure with a penalty on the flow control itself. State variables about 50,000. The effective dimensionality of the parameter dimension. So the parameter space also is discretized. It's actually discretized at the same discretization as the pressure, so the Taylor-Hood elements. Anyway, so there's an effective low dimensional. 128 is the effective parameter dimension. The control dimension is only 18. It's two-dimensional. It's the top and bottom surface. Anyway, so this is the uncontrolled flow. This is the controlled flow, again, under uncertainty in the inflow. So these are very expensive to do. If you just use the full PDE, you would have to, at any given optimization iteration in the optimal control, you would have to evaluate the conditional value at risk. But this is using, I think it's 2,000 samples to evaluate that. I have that somewhere. Anyway, so if you're using the full PDE, you're having to evaluate that objective function. It's very expensive. The alternative is use those PDEs, build a neural network, use that to solve the optimization problem as a proxy for the true parameter to state map. And this is the comparison. So this is what it ends up being. This is the number of PDE solves along the horizontal axis. For the true PDE solution, these PDE solves are used to evaluate the objective function and the gradient for solving the optimal control problem under uncertainty. For the neural network that uses either L2 training or L2 plus H1 training, the number of PDE solves is just used for training. Okay, so those are the differences. Once you build that surrogate, of course, you can sample it to death. So you control the Monte Carlo sampling error, but you have bias from the neural network approximation. With the PDE, there are only so many Monte Carlo samples you can do. So the error there is the variance error. The bias, assuming the PDE is correct, there's no bias. Okay. So what this shows you is the optimal control solution. You take the optimal control solution computed through one of these ways, and you evaluate the exact objective function, the exact cost, which in this case is minimizing the viscous dissipation in the flow. You compute that exactly, so using the full PDE as a way of comparing these three. And what you see is you can get greater accuracy. Oh, sorry, this is the cost. Yeah, so I take that back. This is the relative error. So it's the objective function produced by the approximation, the optimal control error itself, based on a huge number of Monte Carlo evaluations. That's the PDE error is due to the reduced number of Monte Carlo samples. And then we're comparing with a ground truth where we did a huge number of PDE solves. And then the neural network is the error due to the surrogate. And that's compared to, again, the ground truth, brute force, lots of Monte Carlo samples. Okay, sorry, so that's the actual error. And what you see is using the neural networks, especially when you bring in derivative training, because you need to know the derivatives, you're going to solve an optimal control problem that uses derivatives. So that error decreases. And with a smaller number of PDE solves, either you get the same error for a smaller number of PDE solves, or for the same number of PDE solves, well, you get a much reduced error. Okay, so I'll just stop here. There's a last bit about how to improve the surrogates using error estimation, essentially a posteriori error estimation. And I'll just stop with the summary. So, as the parameter dimension increases, generating sufficient data becomes prohibitive. What we're interested in is building neural networks with a small number of training data. And the idea is to use sensitivity information from the parameter to output map to detect intrinsic low dimensional, what you might call the information dimension, and the corresponding dominant subspaces to restrict the neural network to low dimensions, and then you build a neural network in those low dimensions. You can think of this as a parsimonious architecture. And the results are that these parsimonious architectures generalize better. All the errors that we plotted on the vertical axis were all, of course, testing error, generalization accuracy. Easier to train, I didn't say anything about, but solving those optimization problems also was easier if that becomes an issue. And then using this in Bayesian inversion optimal experimental design, extending the framework to learning derivatives in addition to learning the function value itself. So, and derivatives are Jacobians in high dimensions, so that's a challenge, but we talked about how you can deal with that. The optimal design control under uncertainty, those are preliminary results. There's only about a factor of 10x speed up. I think we can do better. I think we can match the 1000x speed ups that we saw with the Bayesian inverse problem in the OED. But we need to look more carefully. It's a harder problem because you have a product space of inputs, the control variables and the random parameters. But still, I think we can do better than 10x. And then okay, so what are the problems? So there's a challenge, and the challenge that I didn't really talk about, I hinted at, is that the viability of this whole idea is based on a low rank approximation of the data misfit, the Gauss-Newton Hessian, or its data space, the J transpose or J transpose J. So all of this is based on having a low rank approximation there, and that gets you into a low dimensional subspace, which you can have further neural network reductions in a nonlinear way, but you need that initial linear subspace reduction. So we've done this on a variety of problems. And these all admit low dimensional subspaces, maybe 1%, maybe 0.1%, depends how big the problem is, up to ordered millions of parameters. But this is not universally true. Information dimension does grow with increasing frequency and wave propagation, increasing Peclet number and transport, increasing Reynolds number and viscous flows. What can be done? That's an open question. H matrix approximations translated to neural networks. Translation invariant approximations. So we've used these to represent Hessians of inverse problems. Can you then extend them to parameterize Hessians using some kind of neural network extension of an H matrix or a translation invariant approximation? Should also mention that for these hyperbolic problems, the Hessian is often a pseudo differential operator. so these Hessians don't admit low rank approximations, but the symbol of these pseudo differential operators does admit a low rank representation. So there's some work that we're doing there. It's still very much in the early stages. But anyway, thank you very much for your attention.
Right, thank you very much, Omar. Are there any questions? Yeah.
Hi, thank you for a very interesting talk. Look, I've worked a lot in geophysical inversion problems, and in particular in Australia in geothermal energy, and working with a whole bunch of geologists. We haven't gone down the surrogate route, mainly because the geologists want to interpret the model that they've put up. But what we found is that the discretization, from the continuous, making it down to a discretization, the solution by discretizing it plays havoc with the shape of the posterior, and that is very problem dependent. It's not with every posterior that it plays havoc. And it occurs to me that this is a way that might avoid that. I wondered if you could comment on, the ability of these methods to avoid that problem that you always get when you're dealing with continuous ODEs and PDEs and when you discretize them.
So that's a good point. And I brushed that under the rug. I didn't say much about that. I just assumed a discretization error to me was just something that's controllable and just that's it. You don't worry about it. But for realistic problems, problems with shocks and problems with complex, discretization can be an issue. Where's Tim? Where's Tim? Tim Sullivan. But yeah, there you are. Who's made a whole book, I think, on this topic. But so ultimately, the errors will be. And I didn't actually say anything about modeling error either. This was just noise observables, although that can include the other forms of, that epsilon can include anything. So in general, yeah, you will have sensitivity to the discretization, and many sufficiently dirty problems don't even have, maybe convergent, climate models. You keep refining the mesh, what do you get? Of course, the parameterization matter. So in general, yeah, one should account for all of these things, but the surrogate itself is going to be trained on solutions of the high fidelity model. So that may have, if that has embedded errors, then they will propagate to the surrogate. There's some results that I skipped over, but essentially the error, and there are some earlier results on this too, but the error in the posterior is of the same order as the error in the surrogate. That's for the Bayesian inverse problem, and for the optimal experimental design, the error in the expected information gain is of the same order, but there could be, the constant could be magnified by the conditioning of the problem. So yeah, unfortunately, yeah. We could speak the discretization. You can for a lot of problems, but yeah, for some problems it's absolutely. It's an issue. Yeah. I like to work on problems and discretizations where we have control over everything. We have convergent methods. In fact, they're high order, and but that's not the real world.
Hello, thanks for the nice talk. I was going to ask about why that would be like an intrinsic low dimensional structure in the input. Would it be related to the grid you're using for the parameter, or?
No, so so people online can hear. So the intrinsic low dimensionality is because often the forward problem is smoothing. The forward operator is smoothing. The solution operator is smoothing, rather, but not just the solution operator, also the observation operator. So there's lots of information. Parabolic problems, there's exponential decay. Elliptic problems, as I said, there's algebraic decay. If you look at the expression for the Hessian, you have inverses of forward operators. So those can be compact operators in elliptic and parabolic cases. Then you have an observation operator, which is further reducing the information. And so when you look at this Hessian, yeah, you'll have the decay. Even a complicated, nasty problem like this Antarctica. So I'll show you one, because this whole talk is predicated on the collapse of eigenvalues. So I should show you at least one eigenvalue collapse. So this is the decay here in the eigenvalues of the Gauss-Newton Hessian, and this is the eigenvalue number. And this is a problem that has order million parameter dimension. And this says, and there's a normalization that you do so that one is, so essentially anything to the left of this, the eigenvectors to the left of this cutoff are data informed. So these are modes, the eigenvectors are modes in parameter space. These are illustrations of them. So this is the first, the seventh, et cetera, up to about 4,000. So this is about what you can expect. This is about the greatest resolution you can get from the data. And anything to the right is prior determined. So this is 4,000 out of order million. So it's 4% of the eigenvalues. No, 0.4%, 0.4%. So that's about, and this is actually, I consider this a tough problem that has a relatively high information dimension. Other problems, it's 10 to the minus 3 or 10 to the minus 4 of the apparent dimension. So this just tells you that if I have surface observations of the velocity in Antarctica and using the physics of the flow, which is a creeping, non-Newtonian flow, then the best I can hope for is this kind of resolution. I don't have much information about what's happening in the interior, and most of the action is along these fast-flowing ice streams out as the ice flows out into the ocean because the surface velocity is changing rapidly, and that's telegraphing important information down at the base. So different problems have different physical reasons why. For model problems, you can analyze it, you can derive explicit, the heat equation, Laplace's equation, wave equation. You can derive expressions for the eigenvalue collapse.
Works. Let me just come check the levels of that. Should be unmuted.
Is it working? Hi. Yeah, seems to. Yep. Okay, perfect. Okay.
Okay, thanks everyone for coming back so promptly from lunch. So the next session, we'll have 2 more talks, each again 45 minutes. And the very first speaker is going to be Claudia Schillings, who's going to talk about one-shot learning of surrogates in PDE-constrained optimization under uncertainty. Go ahead.
Okay, perfect. Thank you very much for the nice introduction. And also thank you very much to the organizers for inviting me. So it's a pleasure to present here my recent research on one-shot learning of surrogates in PDE-constrained optimization and uncertainty. So what I will tell you is how to incorporate the surrogates. We've heard a bit in the previous talk about the surrogates in this setting, how to incorporate them in optimization problems, and how to design efficient methods to solve then the resulting optimization problem. Before I start, I should mention that this is joint work with a lot of people, Philip Good and Simon Weismann, former PhD students in my group. Weser, he's currently doing a postdoc with me, and Francis and Ian from Sydney. Okay, so this is the overview of my talk. I will give a very short motivation. We have seen very nice examples in the previous talk, so I don't have to say a lot about why to use surrogates in design of experiment settings or optimization settings, and why to account for uncertainty at all. So I think you are very much aware of that uncertainty quantification is very important, in particular in optimization problems. And then in the first part, I will tell you a bit about, I would say, the traditional method for optimization and uncertainty, where we use quasi-Monte Carlo methods for optimization and uncertainty, where we focus on 2 very common problems in our community. The first one is the elliptic case with the uncertain diffusion coefficient. And the next one is the time-dependent one, the parabolic one. I will tell you a bit about the analysis we can do in this setting, and also how to derive dimension-independent convergence rates if we assume enough structure in this problem. And then in the second part, I will focus on how to incorporate surrogates in this setting. In particular, I will talk about the so-called one-shot optimization. So I will tell you how to learn the surrogates in an all-at-once fashion, so during the optimization. This has the advantage that you don't have to train the surrogate in advance. You can very much reduce then the input space you have to work with a surrogate, because you don't have to train the surrogates with respect to all possible controls you're considering in your optimization problem. You only have to train it, or you will only train it for the optimal control. And then of course you can use much smaller neural networks, for example, or whatever your surrogate is. I will talk a bit about the consistency that we have convergence result, and I will talk about analysis of the stochastic gradient descent method in this setting, because you will see that it is a very expensive optimization problem in the end we have to solve, and show you some numerical experiments for the toy problem, I should mention. So we want to apply it, of course, also to more nonlinear problems, but the results in order to verify the theory on the toy problem on the elliptic one in this setting. Okay, so that's the plan. As I said, I don't have to say a lot about the motivation. We've seen very, very nice examples in Omar's talk. So let me just tell you a bit about what kind of applications we've been working on so far. So that's the shape optimization. What we want to do here is minimize the influence of manufacturing tolerance to ensure a robust behavior. So if you want to plan, for example, the optimal shape of an airplane with respect to drag and ensure a certain lift, then in the end, you might encounter that the real shape you are producing deviates from the planned shape due to manufacturing tolerance, okay? And you want to take these manufacturing tolerance into account in the optimization procedure in order to ensure in the end that the real shape you produce shows a good performance, and good performance, of course, in a certain robustness measure. Okay, so that's the first example. And then porous medium flow, we've seen the optimal experimental design problem already in the previous talk. So what we want to do here is control of the injection wells to achieve a target state. So that's like a typical optimization problem in this setting. We have a target state. Usually what we have then in the objective is a tracking type function. We need a measure of robustness. So we want to say, under the uncertainties, what is a good performance? Therefore, we want to achieve the target state, for example, in the mean, or we want to control a C bar or whatever in order to ensure a more conservative behavior. So that's what you have then in the objective in your optimization problem. The last one is also an example for design of experiment, the electrical impedance tomography. Here you can think of how to optimize the measurement process in order to maximize information. I mean, we've seen it already again in the previous talk. What we want to do here is we want to maximize the information, and the control is here the measurement process. So the optimization variables are the measurement process, where to measure, how to measure, and we want to choose controls such that we get the most, or we maximize the information. So we have as objective function, we have something like the information gain, or we want to minimize or maximize the variance in the objective function in order to get the most information out of it. So here we use usually objective measure of robustness or objective functions inspired by the design of experiment, like A, or the optimal design criterions you can think of. Okay, so that's what we have in mind. Of course, I've mentioned that already. There's a lot of uncertainty in these problems. And the uncertainties have the potential to render worthless even highly sophisticated methods for large-scale optimization problems. So not taking the uncertainties into account means that in reality, you might end up with a design not showing the performance you expect. We have to take the uncertainties, therefore, into account during the optimization procedure, and uncertainties can arise due to several factors like uncertainty about the model, parameters, and also numerous other factors. Okay, so the common computational challenges in this setting here are the expensive evaluation of the underlying model. That's why we want to use surrogates. And we usually work in a high dimensional, infinite dimensional state and parameter space. So in order to design methods which are efficient in practice and which are robust with respect to, for example, mesh refinement or refinement in the parameter dimension, we usually try to work in the infinite dimensional setting in order to ensure this robustness. Okay, so that means in a very abstract form, we consider problems of this form here. So the optimization problem is the following one. We have a measure of robustness in the objective function. Like, for example, the mean, we want to ensure a certain behavior on average, or we want to ensure a more robust behavior, and then we can consider something like the entropic risk measure or whatever you want here. So this is the measure of robustness. And then we have a penalty usually on the control as well in the objective. So a typical objective function looks like this. We have the measure of robustness telling us what to do with the state. So Y denotes here the state, and the state is uncertain because we have some uncertainty in the model, okay? So think of the elliptic one. I will show you the elliptic one also in a minute in more details. We have the uncertain diffusion coefficient, and for each realization of the uncertain diffusion coefficient, we end up with a different state, and therefore the state depends on the uncertainty U here, okay? And then we want that the state is close to a target state, and we want to ensure this, for example, in the mean, and then the measure of robustness here is just the mean, okay? Furthermore, we usually have some cost on the control. So this is the penalty here on the control. Z denotes here the control. And then we have our model in a rather abstract form here, depending on the control and on the state, and of course also on the uncertainty. We always assume that the model is well-posed. I will come back to this point later on and tell you what I exactly mean by well-posed. But this model here usually is a differential equation, like in the elliptic one, it's the PDE we consider here, or you can also have like an ODE, a parabolic setting, or whatever you have here describing your problem, okay? So then there are mainly two approaches we consider for the optimization and uncertainty. The so-called reduced formulation is based on the solution operator. So the solution operator maps for a given control to the state. So it's the solution of the underlying model, okay? So think of the elliptic one once again. I give you a control, for example, the right-hand side, and the solution operator gives me back the state. Okay, and of course, for each realization of U of the uncertain parameter, I can do the same setting. So for each control, I get back my state depending on the realization of U. Okay, and the existence of this solution operator, that's why I said we always assume that this one here is well-posed, is just ensured by the well-postedness of the underlying problem. Okay, so what we do then is we reformulate this optimization, this constraint optimization problem into an unconstrained optimization problem just by using the solution operator. Okay, so we eliminate the state in our optimization problem and just consider an optimization with respect to the control. Okay, so what we do is we just eliminate this one here using the solution operator, and then the objective function just depends on that. Yeah. So that means thinking of an algorithm to solve this optimization, this unconstrained optimization problem then, well, what we do is in every iteration, we solve the underlying constraint exactly because we use the solution operator. Okay, so there's no state anymore. On the other hand, sorry, in the one-shot formulation, so the idea is very basic. We just say, well, let's keep the state equation, still work in the constraint optimization problem, and simultaneously solve for the state and the optimal control Z. Okay, so that means we have to consider a constraint optimization problem. We keep Z and Y as optimization variables, And that means the constraint is not satisfied in each iteration, only in the limit. Okay, but that gives us more freedom, because then of course we have, from an algorithmic point of view, we have more freedom to design efficient methods to solve the unconstrained optimization problem. Yeah, and in the beginning of an optimization, we don't need exact gradients, for example. So we don't need to solve the underlying constraint exact. It is enough to have just a rough estimate of the gradient, so to say. Yeah. Okay, and that's also the idea to incorporate surrogates later on in the talk. When because in this setting here, when incorporating surrogates, you can see from the very definition of the solution operator, we then need a surrogate mapping from the space of parameters, so the unknown, uncertain parameters times the space of the controls to the solution space. Okay, so you need a surrogate that gives you, for each realization of the uncertain parameter and each realization of the control, the state. Okay, that's a very complicated mapping to learn. Whereas in this setting here, you can just say, well, I have a surrogate. I want to optimize also for, like, for example, the neural network parameters, but I just do it during the optimization. So I just learn this mapping here for the optimal control and not for the bigger space. And that's the main idea, basically. Okay. But as I said in the beginning, before we discuss the details for the one-shot approach, let me say a few more words about the more traditional approach. So what we do here is, and this is now for the elliptic problem, what we want to solve is this, I would say, the simplest optimization and uncertainty problem we can think of. We have the unknown diffusion coefficient over here. So U denotes here the uncertainty, or represents the uncertainty. Z is again the control. This is the right-hand side. So we are linear with respect to the control. And Y is here the state. What we want to achieve in the objective is a certain target, given target state G. And we want to achieve this in the mean. So the measure of robustness I use here is the mean. It's again the simplest choice because it's a linear choice, okay? And then we have some penalty on Z as well. Okay, now in this setting, you can very nicely use the first approach, the standard approach, the reduced formulation, because there's a lot of structure you can exploit here. So assuming, like we always do, we have a certain parametrization of the diffusion coefficient of this form here. And please keep in mind, we are still working in the infinite dimensional setting. So we haven't truncated here this parametrization. This series here, it's the series, not a sum, okay? So the parameter space we are considering here is really an infinite dimensional one. However, by assuming that we have a certain decay here, and by a certain decay, it's on the next slide. So let me just introduce first, sorry for that, the assumptions we need in order to have well-posedness. So what we assume here is, first of all, the summability here of the basis functions and the uniform ellipticity. That means that we are bounded from below and above. And now assuming that we have a certain decay in this KL type expansion, we have very nice properties or a very nice structure in the end we can exploit in order to solve our optimization problem. So what we do in the reduced formulation is we parameterize the input uncertainty as we always do. Then we consider the parametric PDE problem and its weak formulation, and this one over here. We first show the well-posedness of the PDE. So that means we have a family of operators such that this one here holds true, and we substitute then a state by the inverse of this operator, and this operator here, of course, depends in a nonlinear fashion on the uncertain parameter U. We substitute, we end up with an unconstrained optimization problem, and the objective function is then just the one you can see here, where we replace the state by the solution operator, okay? So that means in this setting here, we just have to solve this optimization problem, but of course, This means we have to somehow approximate the mean here in the objective function, okay? And I said in the beginning, so we are working in the infinite dimensional setting, so we need a good approximation of the mean here in order to design then an optimization method. However, since we are working in this elliptic setting, there is a lot of structure we can actually exploit, because we assume the sparsity of the basis functions. And by sparsity, I mean that this one here holds true for a p between 0 and 1. So that means basically, so connecting to the previous talk, that we have a lower dimensional setting, because we have just a few dimensions really mattering. First of all, this is the KL expansion, but there are results that we have the same behavior then also in the solution, okay? So that means this structure we impose on the parameterization of the unknown parameter ensures that we have a low dimensional structure also in the solution, which we can exploit in order to come up with a discretization approximation of the mean in the objective function by quasi-Monte Carlo points. Okay, so what we can then show is the following. So we compare the optimal control of the original problem without any discretization to the one where we truncate the series after S terms and use an endpoint quasi-Monte Carlo method to approximate the mean in the objective. And then we can bound the difference between these two controls in the following way. So we have here on the right-hand side the truncation error. So we know all the constants in front of, we know the truncation error. And we have here the quasi-Monte Carlo error, and the quasi-Monte Carlo error is in this setting dimension independent. But just to connect to the first talk, it is dimension independent because we have a lot of structure, okay? We know that it is basically a low dimensional problem. And we use different norms, okay? So we account for this decay in the higher dimensions by choosing just the right norms in this setting. All right, so that means we have a very nice structure in this elliptic setting. And of course, I haven't talked about the discretization of the underlying model at all, the spatial discretization. You can use whatever you want for the spatial discretization. Basically, you just use the triangle inequality, like for example, finite elements with the linear ansatz functions. Just use triangle inequality and get an additional term here with the weight you get for the finite element approximation. Okay, so that's consistent. What's nice about this result, so we could generalize to the setting where we still work with the, in our case, Hilbert space, states, valued states. So that means we don't have to do it for every discretization, spatial discretization of the underlying model. It's just you can use whatever you want and get your weights you expect from there. Okay. Just to show you that this is not only possible for the very simple elliptic one, we could generalize also to the parabolic setting, so the time-dependent setting, and also have similar results for a nonlinear risk measure. We considered here the entropic risk measure, giving you a more conservative solution. Okay, so this is the result in the parabolic setting. It looks very similar, so basically it is the same. It was quite technical to get there. However, what you get here is a similar truncation or the same truncation convergence, and also the same quasi-Monte Carlo rate. Okay, and just to show you some pictures, or maybe how much time is left actually? Is it just? Okay, and then I have to stop. Okay, including questions. So I can show you the, the video later on. It's just to ensure that it is a non-trivial example, because with the optimization and uncertainty, we sometimes assume that the uncertainty is so little that the controls you get are actually the ones you would get with the mean. Okay, this was just to ensure you. Okay, so we considered a uncertainty large enough so that the controls, the resulting controls, indeed differ, and it's worthwhile to consider the uncertainty in the optimization problem. Okay, so let's come back to the incorporation of the surrogate. So that was for the reduced formulation, and it works very well for problems where you have the structure, everything is known, and you can easily compute derivatives, whatever you need, because the analysis, I've hidden it, that here, the analysis is very much based on the adjoint approach, because you need the all the bounds I've showed you on the adjoint, and then you get also the convergence of the controls. Okay, so let me summarize once again the reduced formulation. So we parameterize, we consider the parametric PDE problem, show well-posedness, use the solution operator, and then solve the unconstrained optimization problem. So how can we incorporate now surrogates efficiently in this setting? Well, what we do is, instead of using the solution operator here, we want to use the surrogate approximation. Okay, so sorry for that. We want to use here our surrogate, and theta are now the parameters of our surrogate, like for example, the neural network parameters, the weight and the biases. Okay, so that means instead of using the real solution operator, we use now the surrogate. However, in this reduced formulation, that's what I said in the beginning, we have to train a surrogate mapping from the parameter space and the control space to the state space. Okay, so you need to have a surrogate giving you for each realization of the uncertain parameter and feasible control the state back. And that's really expensive. So we tried that in the elliptic setting. We kind of failed, to be honest, and to reach a good accuracy, because usually we don't assume enough structure on the control. Okay, so there's now, of course, you could say, well, I can parameterize, and then you can easily do that. But we usually assume no structure at all. It's usually in an infinity control, or yeah, depending on your problem, but there's no structure you can exploit. So that means you need like a huge neural network in order to approximate this mapping here with a good accuracy. Yeah. And now what we want to do instead of doing this in advance is, well, we can just use the one-shot approach, because in the one-shot approach, as I said in the beginning, we don't substitute the state. So we don't eliminate the state using the solution operator, but we just keep the state. Okay, and we use now a very specific strategy in order to solve then the resulting constraint optimization problem, because we use here a penalty approach. This is not, from a numerical point of view, this is not the best you could do, because this is a quadratic penalty and we have to send this penalty parameter here to infinity. So in a basic numerical analysis course, you usually learn that's not the best you can do. However, there's a nice connection to the Bayesian approach, which gives us the possibility to interpret this penalty parameter here as a model error. Okay, I will come back to this in a second. And this is very nice, and I think that's worthwhile to consider this approach. And we have also on the algorithmic side, we have an efficient way actually to solve this sequence of optimization problems then. Okay, so what we do, we consider this penalized formulation here. We have to send gamma k to infinity, and then have a sequence of solutions of the optimization problems, zk and yk star. And we know under suitable conditions, or I will show you in a second, that we will indeed converge to the solution of the original problem. Okay. Now, this is now the connection to the Bayesian framework, and that's why I think it's worthwhile to work in this penalty approach. Because we can think of the forward model here in the penalty approach by a Bayesian viewpoint, and think of it as a vanishing noise model. Because what we have here is this additional constraint, okay? So assume we have some model noise, and we always have some model noise, okay? So in this setting, the simplest one, you can think of just additive normally distributed noise, where then you recover the optimization procedure by considering this vanishing noise model. So you scale your noise covariance by a parameter 1 over gamma. And if gamma goes to infinity, then the noise goes to 0. Okay, and this is exactly the connection to the penalty approach, because here you want to send gamma to infinity and recover the solution of the original constraint optimization problem. Okay, in the simplest setting, that's no surprise at all. However, this gives you the possibility to model here the model uncertainty in a much more interesting way, and a way suitable for your application, basically, because but you don't have to use this model here. This gives you basically the norm you need to consider here, okay? And you could think of this parameter gamma here not only as a parameter, as a scalar, but you can use a function as well, okay? And this is nice because then you know that, for example, in some areas, you know, your model will be right. So you could have a spatially dependent parameter function gamma here going to 0 in these areas, and in the other areas, you know, well, there will be errors, so you can account for this actually. And I think that's why I like this penalty approach. On the other hand, you should keep in mind that's not the most stable way to solve constraint optimization problems. Okay, yeah, so that's what I just said. So that's the connection to the penalty approach, and that's why I think it's worthwhile to consider the penalty approach in this setting. Okay, now the surrogates. So far, we haven't included the surrogates at all. So let's replace the state with our surrogate. So now the state depends on the surrogate parameters, theta, like the neural network parameters. We want to do it, well, you all know cheap evaluations of the surrogate in the end. The surrogate here is learned on the fly. And I think in particular for the design of experiment problem, this is very nice because it's in the end, it's trained for the optimal parameters and what you want to do after the design of experiment optimization, but you want to solve the inverse problem and you have a surrogate, so to say, for free, if everything went well. Okay, so that means the optimization problem we consider here, well, instead of keeping the state here, well, we have now the surrogate parameters theta as optimization variables. So z and theta are now our optimization variables. We have this penalty term ensuring that we can recover the original constraint. I should say that sometimes we have to add also a penalization on the parameters theta here, in particular when using neural networks in order to stabilize everything. But it's not limited. Yeah, please ask.
So when you're talking about the surrogates, is it the same U or is U now truncated?
Say it again, sorry.
We're talking about the surrogate.
Yeah.
Is your U still infinite dimensional or has it ended?
Yeah.
Surrogate is
yeah. It's still infinite dimensional, and theory, the consistency theory I will show you in a minute, holds true in the infinite dimensional setting as well. But at some point, of course, for the surrogate, you have to truncate. But yeah, consistency is still true also in the infinite dimensional setting. Yeah, and of course, it's not limited to neural networks as a surrogate. You can use your favorite surrogate. And also in the elliptic setting, I will show you some numerical experiments in a minute. We know a lot about the problem. We know how generalized polynomial chaos behaves, and we will see that this is also the choice you should consider for the elliptic one, because well, it's linear in this setting. And you have nice convergence results and similar to what a neural network can do in the end. Okay. So the consistency result, we need, of course, a bit of assumptions, but it's quite standard theory for penalty methods. Under suitable convexity assumptions on the objective and constraint. And then the problem we have with a neural network, for example, because you can't ensure the convexity assumptions anymore, but with the generalized polynomial chaos, for example, in the elliptic one, we can check all the assumptions we need here. We have the following consistency results. So comparing or measuring the difference between the solution of the original problem and the one we have here when discretizing or approximating the mean here by just a plain Monte Carlo approach, and considering here the penalty approach. We have consistency in the sense that if gamma goes to infinity and n to infinity, we actually converge. However, we can see here that there's a coupling between gamma and n. And that's also what we expect actually, because well, we increase here the variance. So roughly speaking. So if gamma goes here to infinity, the problem is more difficult to solve. So we increase, so to say, the variance here in this setting. And therefore, we encounter a coupling between gamma and n. So that means for example, for the choice that we choose gamma to be n to the 1/4, then we get this convergence rate here, only depending on n, and we have an explicit expression for the constants here as well. So, and that's maybe referring to your question. So this still holds true in the infinite dimensional setting. Okay. Now, but in the end, we have to solve the optimization problems, and there are now two problems. But with the penalty approach, you always assume that you compute the global minimizers of the individual objective functions of the sequence of objective functions. That's not what you want to do in the end. That's too expensive, okay? And furthermore, you don't want to compute gradients if you're in a gradient-based method with respect to a large n over here, okay? That's also too expensive in each iteration. So what we do then is, the first trick is well known to the optimization community. We just increase the penalty parameter during the optimization, okay? So instead of solving the optimization problems for like 1,000 different values of gamma, we just increase it during the optimization and send it to infinity, or close to infinity, like large. And then we use a subsampling strategy. So that means we don't want to compute here gradients with respect to the optimization variables for all n. We just use subsamples here. Okay, so that's the idea from stochastic gradient method. We have convergence result, and I will talk a bit about convergence results for the stochastic gradient method when increasing gamma k during the optimization in a minute. But now we have also results for the ensemble-Kalman inversion. You can also think of the ensemble-Kalman inversion as a derivative-free optimizer. And we can now use it also in this subsampling setting. And this is very important in the end to really solve the resulting problems. Okay, but since I will show you the numeric experiments in the elliptic setting, we can easily compute gradients via the adjoint approach. So we can work with stochastic gradient methods. Okay, so what we have here as a penalized stochastic gradient method with adaptive penalty parameter. Well, this is the basic stochastic gradient version. We just increase the penalty parameter gamma here during the iteration. Okay, so we send it to a large value. And what we can show, once again, of course, on a suitable choice of the step size and on a suitable assumptions on the forward problem, like in the elliptic one with a linear surrogate, we can check all the assumptions. Then we have indeed convergence, because this sequence of constants here goes to 0 as n goes to infinity. And as usual with the stochastic gradient method, we have an explicit expression for all the constants here, and they depend basically on the convexity of the underlying problem. Okay. Now, I think I have to come to an end. So just to show you some pictures, we did some numerical experiments in our toy problem. With our toy problem, so the elliptic one, unknown diffusion coefficient. This is then the sequence of penalized problems we have to solve. We use a Monte Carlo discretization. We use TensorFlow's implementation of atoms. So this is not the perfect match to the result we have here, because Adam used more tricks in order to get a good performance. However, it's quite similar. And we use Legendre polynomials as a surrogate because we know there's enough structure. So Legendre polynomials work well in this setting. And we use a neural network as well. However, with the last one, this is a nonlinear approximation. We can't check all the assumptions we need for the consistency and the convergence result. Okay. So the first one is on the consistency. Varying, first of all, the sample size, this is the basic Monte Carlo error. You see here then varying the penalty parameter over here. From the results, we have the rate, so that's just what we expect from theory, and then varying both simultaneously, as I said, because the convergence is coupled via the constants here, we can actually see the predicted convergence rate in this setting. And then for the optimization problem, so what we do here is we have our surrogates, Legendre polynomials up to order 1, 2, and 3, and the neural network. And we compare it to a full solution of the original problem. So please keep in mind that at some point, you will just see the surrogate error, okay? Because we can't expect that we drive this error towards 0, because there is just the approximation error from the Legendre, from the polynomial chaos approximation on neural network, okay? And what we can see here is, well, what we expect, as I said, because at some point we will just see the surrogate error. Legendre polynomials of order 2 behave quite similar to a neural network. And we should keep in mind that if we know that some of the surrogates, like a generalized polynomial chaos, which is linear in this setting, behaves well, then they might beat also the neural network approximation, okay? And then we have here the error between the states, similar to what I just said, so quite expected what we see here. The mean squared residual error just of the constraint, and the other one is with respect to the first, the target state error. Okay, so I hope I could perfect, okay. Stay in time. And so what I showed you is with the standard approach for like the standard problems, the elliptic and the parabolic one, we can have a nice convergence theory for quasi-Monte Carlo, for example. Quasi-Monte Carlo compared to sparse grids, they have the advantage that for the optimization, they preserve all the structure because you have an equal weight quadrature rule, okay? So like Monte Carlo, for example, but with a better convergence rate in this setting. We have also the analysis for nonlinear risk measures like the entropic one. This is still a smooth one, I should say, because quasi-Monte Carlo, they need the smoothness. Then I presented a quite flexible framework to train surrogates during the optimization. And the main advantage to do that is that you don't have to train the surrogates in advance. You don't have to use big surrogates or neural networks in order to have the approximation accuracy. You just train them then in the optimal control in the end. And for example, for the design of experiment, I think the main advantage is you get a surrogate for free for the inversion process afterwards. Okay, so thank you very much.
Thank you very much, Claudia. Any questions? Yep.
Thank you very much for the talk. Did you try for the model error that you put with the penalty approach? I would have thought that maybe we could use some kind of augmented Lagrangian framework so that actually you don't have this problem, this issue with gamma.
We should definitely do that. So I always get this question, and we should definitely, because it's the obvious question, that's from a numerical point of view much more stable to do that. There's not like a straightforward connection to the Bayesian approach. I still stick to the Bayesian connection because I think In the end, you should really include model error and not drive the penalty parameter towards infinity. And that's like the nice connection, but I totally agree. We should try to establish some connection.
Because in data assimilation, sometimes we penalize the model and then still have the Lagrange multiplier with respect to the model.
Yeah, I would love to discuss more details. Yeah, it was, yeah.
Any other question?
So it's very nice, Claudia. I like this idea of essentially, asymptotically satisfying the PDE in this one-shot idea, extending this to the notion of a surrogate. You asymptotically construct a surrogate, so you never have to construct it over all of the Z space.
Yeah.
And this is nice. What I missed was when you introduce the surrogate in this weak way. How do you benefit? You're still, because the A is the full PDE operator, so you still have to compute that. What is there a reduction, introducing the surrogate, how does that reduce the computational cost compared to weakly enforcing the PDE? I mean, enforcing it through a penalty.
Yeah, so I'm not entirely sure if I got the question, so maybe we can go back here. So maybe here. So instead of working directly with this operator, here we use the surrogate then in the end. And you mean what you gain in performance, or?
I mean, in the one shot, yeah. In the reduced formulation,
yeah,
you have the mapping U to Y represented, but then as you argued, that has to be predictive over the control space.
Yeah.
It's challenging. Instead, you said, no, we're going to do it in the one-shot setting.
Yeah.
So in the one-shot setting, you don't solve the PDE. You try to minimize the squared residual.
Yeah,
PDE,
exactly.
So you do it asymptotically.
Okay.
That's
yeah.
nice. So, but then you introduce the theta, Y
Yeah.
sub theta. And so how does that representation of Y using, for example, orthogonal polynomials or neural network, does that reduce the computation compared to just keeping Y discretized using, let's say, finite elements? I mean, no, this has to be a representation of Y in parameter space.
Yeah, exactly. So that's the difference. But of course, I agree for some of the examples, and like for the elliptic one, everything is well known, and you should use your gradient computation via adjoints and finite element approximation you always use. However, in some cases, it's just you don't have a good method to discretize in space, and you don't have a good method to somehow approximate. So it's always I should mention, it's always an approximation of the solution operator at this point. And sometimes you just want to use a surrogate in this setting, and you can think of the finite element approximation also as a surrogate, but just in a different space. Yeah, but I totally agree. So in the elliptic one, it's not clear why to use a surrogate at all, because you have like the convergence from the finite element approximation in space, and you can just use like the traditional approach. But yeah, I totally agree. But I would,
The question is, you don't want to do it a priori because now it has to be predicted over E and Z.
Yeah.
And instead, you can do it on the fly.
Yeah.
And train it. You have to represent that parameter space. You don't want to just a Monte Carlo evaluation.
Yeah.
And instead.
Yeah. And I would also think of the finite element approximation as a surrogate, but just in a different space. So, and then it all fits into the same framework. And then, yeah, of course, it depends on the surrogate and on the model what's the best way to do it. Yeah.
Okay. Thank you.
Yeah.
Okay, the microphone is down again. So thanks, Claudia, again.
Thank you. Yeah.
Yeah, that works. Okay. This one or this one?
Choose this one. Can I share? This one. Okay, so that's working. Sorry.
Would you prefer this one or this one?
If possible, this one. Let's see if we can get it to work. Doing anything? Now it's working. Yes. Yeah. Okay.
Great, thank you. This one, okay. Very temperamental microphones. Okay, well, thank you very much. So the next speaker is Marie-Therese Wolfram, who is a professor at Warwick, who will tell us about inverse optimal transport. Please go ahead.
Thank you very much. Thanks for inviting me. And yeah, first I want to apologize. So when I was invited, I was like, okay, I'm not an expert on digital twins. I haven't worked on those. I learned now what they are. And from my understanding, what probably feeds most of my work into this field, it's my work together with Andrew Stewart and currently ongoing with Andrew Duncan on inverse optimal transport. But as a disclaimer, I'm an applied mathematician, so applied PDEs. So yeah, it's not the perfect fit, but I hope you find it interesting. Okay, so as I said, this was a project that started with Andrew Stewart a few years ago, and I've been looking into that also together with Andrew Duncan, who is at Imperial College. And what I'm going to report about today is what are inverse optimal transport problems and why are they interesting, and how I think might connect to digital twins. And when I talk about optimal transport or inverse optimal transport, then you'll find this problem in different settings. So at the beginning, I will try to give you a motivation how I came across the problem and what other applications which fall into inverse optimal transport have been considered. And then I will talk about the Bayesian framework and how you can use it to solve this problem. Okay, but just to start, I should probably tell you, okay, what is optimal transport? So some people or most people know, I think, the Wasserstein distance, which is nowadays very, very popular to compare or measure differences between probability measures. And it goes back to optimal transport. So the first formulation of optimal transport goes back to Gaspar Monge, which was 17 something. So don't get me, nail me down, but he asked a very general question. And it's this very famous picture. If you have a pile of dirt and you have a hole, we call these two probability measures mu and nu, and ideally they have the same, so they have to have the same volume. Then if you have given some kind of cost function, so which tells me how much it costs to move mass from a location X, where my probability measure or some X, X in space, to a location Y, then I want to find the transportation map T, which minimizes this cost. And you want to choose a transportation map which preserves the mass. So T push forward nu is nu. So you want to make sure that the mass that you take from your measure mu, that you dump it in the hole. Okay, so this was the first formulation of Monge's problem, and he made some progress, but it's got quite a hard problem. And if you're interested in it, I mean, there's lots of mathematical literature, but it was not until 1940 until Leonard Kantorowicz looked at the problem, and he looked at a relaxation. So instead of looking for a transportation map, what he considered was that he wanted to look, or he was suggesting for the looking at the similar problem, but now you are looking at transportation plans, which are probability measures on the space X times Y. And so you want to minimize the cost of transporting mass from X to Y among all transportation plans. So pi is now a transportation plan. And the transportation plan has to be from the set of admissible solutions. So, or admissible transportation plans, which means that you have, if you project transportation plan onto the spaces X and Y, then the push forward has to satisfy the marginal constraints. So in the sense, now pi of X and Y tells us how much mass was transferred from a location X to a location Y. And why is this a relaxation? Well, it allows us to split mass, while in the previous setting, the map T of X tells us where the mass located at position X was moved to. Pi of X and Y tells us how much mass from location X was moved to location Y. So we can split mass, and that makes the problem much easier. I mean, much, but yeah, significantly. There was lots of research on that problem. And if you're interested, there are books by Villania and Filippo Ambrogio looking at the theory of this problem. However, for my setting, I'm actually going a bit simpler. And what I'm going to consider is that I'm looking at discrete optimal transportation problems. So now we're replacing the measure mu and the measure nu by two probability vectors. I call them P and Q for the time being. And I have a given cost matrix, C, where each entry tells me how much it costs to move mass from a position xi to yj. And I want to find an optimal, I call it here now transportation map, but it's again, this is a matrix which minimizes the cost here among all admissible transportation plans. And again, this it's just a translation. So again, you have to satisfy the marginal constraints. Okay, this problem is much easier, and I'm going in the following just talk about the setting where I have a discrete two probability vectors. I have a given cost matrix and the forward problem. So if I solve the discrete optimal transportation problem would be, okay, I want to find the transportation matrix T, which is optimal for all for a given cost C. Okay, so far so good. So now, but what if I have some kind of observation of T or pi, and it might be noisy, but I don't know the cost. And that's what I refer to as the inverse optimal transportation problem. So instead of knowing now the cost functional and my marginals, the other way around is, okay, given some kind of approximation of a transportation map applying T, can I infer the underlying cost criteria? And why is this interesting? Okay, so there are a couple of applications, and you can extend this. So the longer I work on it, the more the more applications I learn of. So this was something that was pointed out by some referees when I was writing the paper with Andrew Stewart, and he was like, actually have a look at the marriage market problem. So the marriage market problem is a problem in economics, and it looks at the problem of given some two marginals, P and Q, you can call them male and female, and you want to find a matching, a stable matching between these two marginals. And in the marriage market problem, so what Alfred Gallichon and Bertrand Saloni suppose or assumed is that find a stable matching between male and female, you want to maximize, since we're now in the economist setting, we maximize, we don't minimize, but put a minus in front, you can minimize the social surplus. So the social surplus would be, okay, what's the benefit if I'm marrying someone, for example, who has a higher income, a higher social status, better education. So you want to maximize this social surplus. And what they also did, they added a functional here, which is, you might notice this is entropic regularization term. So the epsilon here is a small parameter. So you add a small term. A nice advantage of this is it makes your problem convex. And I will talk a little bit about this later. So this is some kind of regularization term, but what in general, what they wanted, they were like, okay, let's maximize the social surplus by matching females and males in a population and try to figure out, okay, what is a stable matching? And then they went back and had a look at the inverse problem. So what they did was they were interested in the question, how did the legalization of abortion, so Roe v. Wade in '73, affect marriage behavior? And what they did is they looked at two data sets. So you have the census data from 1970 and 1980, as well as the marriage records from the following years. So here you have the distribution of male and female in certain age brackets, as well as the marriage data. And what they wanted to identify, so they assumed that this matching is the marriage data, they wanted to identify the surplus coefficient, so this coefficient C. And so if you go to this report, then what you see here on the left is for male and female, this is the difference of one of the certain utilities. So I think there are 3 of those for male and female. And what you can see is this is the relative difference between the 2 years. So here you plot the difference between 1970 and 1980. And what you can see is if you go according to age, that the coefficients, there is a significant difference, for example, for male in the age bracket from 20 to 30, while for female, apparently it didn't change the social surplus that much. So they concluded there was some kind of change in the incentive to get married between 1970 and 1980. I'm not claiming that this was true, but this was the first problem where I ran into it. And so the question here, yeah, okay. Given marriage records, can we identify, for example, a change in the social surplus or in the marriage behavior? Then there are other applications which go back to image sampling. So in this case, what you want to do is that you have in this case, and given some observations. So here my orange dots, they are observations of histogram. And if you, for time being, just ignore the math here. If you assume that you want to find a kind of a geodesic, so given some observation of histograms, you want to define the underlying cost, which, so to say, find the best geodesic matching these observations. Then what you want to learn, if you interpret these histograms as probability vectors, which this interpolation here lives in the Wasserstein space, you want to learn what are the weights of the underlying, it's kind of, yeah, it's nodes on the Wasserstein space, so that you find the best geodesic in the Wasserstein space matching your observations. So in case of just using here, what you do is a Euclidean distance, and between the first and the last observation, you're trying to match or bend your space in a way that you match your geodesic, that it fits observational data in the best way. And what they did is, in principle, if you have some kind of interpolation, so between consecutive or your, these are the points and your observation, you try to minimize the loss plus some regularization to find this kind of nice curve. This is, however, so this is work by Marco Couturi and other people. It's just to kind of give you an idea. So in this case, they really try to find the underlying metric of this space. So how do I have to spend my space to fit observations? In this case, they are histograms. And the take-home message from that is, yeah, you choose some loss, you have observations, you minimize some loss, you have to add some regularization, but still, I mean, this problem is severely ill-posed, and so it's even not convex. So if you go at that, then expect to have some problems, but these guys were interested in trying to solve this problem.
What is J? Because you're summing over I and J.
I and J, oh, wait, oh, it should be I's, sorry. The problem that I looked at and I started to look at was from a discussion with colleagues from the Wittgenstein Center at the Austrian Academy of Sciences. And what they explained to me was that they are interested in international migration flows. So if you're working on international migration flows, what you want to understand is, okay, why people move from A to B? And what are their incentives and what are they going to do later on? And if you look at the data, then you can go to the databases. So you can go to the Eurostat, so European, from the European Union, you can also go to the United Nations. So for every country in the world, you find some what is called, so there are two types of data, but I'm giving you now one. This is the flow data. And the flow data tells you how many individuals moved from one country to another in a given period of time. And if you look at this data, it's surprisingly bad. So first of all, there are no international standards. So up to this date, I'm not aware of any. And these are some data which was collected from 2002 to 2007 in the European Union. So if you look at this data, so R means what the receiving country reported, and S is what the sending country said. So, and if you look at some countries, you have a very nice match where you say, okay, Denmark said that so receiving, Germany said 2,687 people came from Denmark. Denmark reported that 2,612 moved to Germany. Well, sounds somehow reasonable. There is some difference. You can go to Poland. Germany said 136,000 people came. Poland itself said 14,000 came. So what you can take home from this is, yeah, there is some mismatch in here. And the question is, but what if you want to identify or want to interpret this flow data as a transportation map, and you would like to understand the underlying incentives? So why are people moving from country A to country B? And an incentive could be, for example, you have better living conditions, or you want to understand like kind of why does people move the way they do. But that's the data you have. It's not very good. What demographs usually do, this is a nice plot by Gallardo. So they usually try, so they don't necessarily interpret it as an optimization problem or optimal transport problem. They have simpler models, but they produce this beautiful graph. So here you can see how many people moved from one country to another. So these are the migration flows. And what they in the end try is they try to make predictions based on age and kind of, yeah, what to expect in the coming years. So this was the demographic data. And when I looked at it, I was like, okay, what if I interpret something like this as a transportation map? And can I infer the underlying cost or incentive? And that's what I'm going to talk about in the rest of the talk. Just one more picture, and it's a bit blurry. I'm very sorry about that. This is a really bad resolution. It looks better on my computer. I'm sorry. So if you're interested in migration flows, you might also want to go to the Eurostat. So the Eurostat gives you basically the transport or how much food was moved from one country to the other from 1961 on. So you can choose, for example, bananas, and it will show you how many bananas moved from Brazil all over the world for different kind of, for all years. So you get commodity flows for basically all agricultural products. And so the question could also be, if you look at two snapshots from two times, so this is 2000 versus 220. I mean, it's very hard to see. This is the US, over here is Europe. And one can see that some countries kind of gained popularity while others, they lost it. And so this is kind of giving one also maybe an idea, how do transportation networks change, and what are the incentives to move agricultural goods from one place to the other. Okay, so that was a long introduction, but I hope I convinced you that these problems are interesting. And now what I'm going to continue with is, okay, if I have an inverse optimal transportation problem, how can I solve it? And first of all, since I'm a mathematician, I'm setting some notation, but that's just for writing things down. By PNN, it's just a set of probability matrices, same for the vectors. And with these two M and these are mappings. And later on, when we sample, then it's often more useful that you sample and later on normalize them to make sure that your elements lie in the right spaces. So these are just some nice technical details, but just to set the scene. Okay, so just to summarize what were we interested. So the forward problem, as I said, is I have given two probability vectors P and Q, and a given cost C. And now I wish to find the optimal transportation map with T, so I call it T star, which maps or transports P to Q at the minimal cost. So this is the forward problem. And if you go to the literature, then the question is, okay, these problems, they are not cheap. So if you want to solve this, up to the early 2000s, there were very few algorithms. And so these are the auction algorithm, Hungarian algorithms. So there were some, but it was just a very computationally costly problem. If you have, for example, P and Q being very high, being high dimensional, you pretty fast ran into problems. So what was done afterwards, or it was like in the early 2000s, Couture rediscovered a matrix rescaling algorithm. So it's now known as Sinkhorn algorithm. And there's a very nice paper from the TU Munich about how many times this algorithm was rediscovered. I think at least 5 or 6 years, 5 or 6 times. So he claims that things that get rediscovered are really important. And well, I think he is not wrong. So the trick is, and we have seen this, is that you add this entropy term. And what is the nice advantage? If you add, so you regularize your problem, then your problem has now a unique minimizer, since your minimization is now convex. And the really nice thing is also you can solve it very efficiently using what is known nowadays as Sinkhorn algorithms, which only involves matrix vector products and rescaling. So this converges really fast. And after that, really, OT became much more popular. Now you find Wasserstein distances and all these kind of things being used. So we will either in both cases look at both formulations. So we will look at the not regularized problem. So then you have, if you want to solve this, use a linear programming algorithm, while if you solve OT epsilon, you just use the standard Sinkhorn for the forward problem. And if we go to migration flows, then you also have to somehow relate, for example, some kind of underlying network structure. So we want in the end, as I said, interpret this demographic data or use it and see if we can infer the costs to move along a network of edges which connects, for example, countries. And since the first work with Andrew Stewart was a bit more on a toy problem, we tried to get this to work. We thought, okay, let's start very simple. So we assume that individuals move from one country to another and trying to minimize some given costs. And these costs depend on some structure which relates to the geographical position of these countries. So each of my countries is a node. And then you have this origin destination matrix. So my transportation matrix can be interpreted as very noisy estimate of a transportation plan arising from the corresponding OT problem with an underlying cost C that depends on this graph structure. Okay, so graph, we assume it's directed. Each country is represented by a vertex. And I know we made it much too easy, but we said, okay, countries and vertices are only connected if they share a border. So you can only move from A to B if they're connected. So you can't fly, I'm sorry. And the total cost of moving from one country to another corresponds to the sum of the individual costs moving from one country to another along one edge. So that was basically the cost. And I don't have that much time. I mean, you can write down the adjacency matrix, which tells you which countries are connected. You can then take the null zero entries, give you a vector, and then define this mapping which gives you the cost of moving from one country to another. And if you go to the literature, in the end, it's solving a minimum distance or minimum cost problem, which always corresponds to Dijkstra. So by E of F, I usually, F is now the non-zero entrance of our adjacency matrix, and E just gives you the solution of Dijkstra's algorithm. So the minimal cost of moving from a country I to a country G. So if you write down now the forward OT problem, then I'm now, instead of using P, Q, and C, I will use the variables U, V, and W, which are later on then mapped into, so F is my forward operator, is the solution of the OT problem. Then I take U, V, and W, so they don't have to be probability vectors. I map them in the respective spaces, and this gives me my forward operator, which I call curly G. The same is true if you have some graph-based cost, because then W is not a cost matrix, but this forward operator E, which just takes the non-zero entrance of the adjacency matrix and maps them to the cost. And then we want to determine P, Q, and C from some noisy observation T, which either solves the not regularized or the regularized problem. And we're going to use the Bayesian framework for that. Okay, so if you are just counting numbers or doing, I mean, that's really bad for a mathematician because usually we can't count, at least I can't. But you can have a look, okay, is this problem in general over or under determined? And if you start playing around and I look at the given cost matrix C, I always put a Z bar on the diagonal, which means I don't allow individuals to stay. For this kind of very simple exercise, I was just interested, okay, what happens when is the problem well posed or overdetermined and when is it underdetermined? So if I assume that C has a Toeplitz structure, which means it's kind of a tree diagonal, just to give you an idea, makes absolutely no sense in the sense for demographic problems, but we thought, okay, let's play a little bit. Then if n is larger than 3, the problem is overdetermined, so I would expect that I should get quite good results. However, if I assume that C is non-symmetric, then you immediately see for n larger than 2, you are underdetermined. And okay, so let's see how well we do in this case. If you have a graph-based matrix, a graph-based cost, then it depends on the degrees of freedom of your adjacency matrix M. So how big the costs are related to this, but you can also write down a condition. So we thought, okay, let's play with this. As I said, it was kind of a starting point. What happens in the overdetermined case, I would expect we do very well. In the non-symmetric case, we should quickly run into trouble, or at least our results should get much worse.
Sorry.
Mm-hmm.
When you don't want two countries to communicate, you put the cost to infinite then?
Yeah, very high. So what we then did is simple. We said we assume that the transportation map, it's a noisy observation. In the simplest case, you add some Gaussian with 0 mean and variance. Then you can define the misfit function, and you use Bayes' theorem, assuming, okay, so what is the probability of observing U, V, and W, which corresponds to our marginals and C, given some observation T? Well, we all know that we have our likelihood and our prior information. And so if we want to write this down in the end, you can, in this very simple case, if I assume, for example, that U, V, and W are just uniformly distributed, I can compute the posterior distribution. It's just given here by this exponential times my indicator function. And then you can sample from this posterior distribution. And to do that, I don't think I have to tell you how to do it. We used just random walk metropolis within Gibbs, which means, okay, looks ugly is not very difficult. You suggest and propose a new value. You check, okay, am I doing better or not? Accept or reject. And I do this for the marginals and I do this for the cost. So this is what we did in the end, and this is not very insightful. Okay, so I told you that for Toeplitz cost, I'll go to the next slide because then we have some time. We would like to see, okay, how well am I doing? And what we did here is that we had a 5x5 cost matrix. So I knew the ground truth, and I generated my transportation map. And then I was looking, okay, assuming that I wanted to reconstruct or to quantify or estimate my parameters, for example, in C, U, and V. So here you see the third component of U, which is, as I said, if n was equal to 5, the third component of V, and the same for the cost, just one entry of this cost matrix. And what we did is we looked at 3 different settings. So LP means linear program. So I'm solving the problem, the OT problem with epsilon equal to 0, so I don't regularize it. However, if for the forward solver, it speeds up computations. I can play around with, am I going to choose a synchron solver? And the red one there, I added a small regularization, while for the gold plots, the regularization parameter was larger. The black line gives you the exact values. So you see here, these are my exact values. And what you take home from that is, okay, if I solve with the linear program or with the synchron with a small regularization for parameter, you do fairly well. You pick up the value fairly well for this toy problem. As you increase the regularization parameter, this is this epsilon. I mean, the problem is by adding the regularization, you blur out your transportation map. You generally run into problems of identifiability. You see, it's kind of not as nice as it was before. You can go to non-symmetric costs. So in this case, n was chosen again to be equal to 5. We generated our data again with some ground truth. And I show you again 3 plots from the marginals, the second component of U and V, as well as C1, 2. We added a bit of noise, and the black line gives you the exact value. Of what you get is, we haven't even tried with large epsilon here anymore. Red and blue were the linear program and the synchron solver. Again, for the marginals, we did fairly well. While if you look at this already kind of indicates identifiability issues, because if you scale this basically gives you a uniform distribution. So in the end, the problem is underdetermined. You're running into troubles and you're having a much harder time to pick this up. We also played around with graph-based costs. So as I said, if I generate, for example, myself, a made graph with 5 vertices, 12 edges, you play and you generate a transportation map with a certain noise. You can do the same again. What is shown here is the posteriors. They pick up the marginals fairly well. Also the cost. So in this case, this was ill-post, but not as ill-post as or underdetermined as the previous example. So we did fairly well. But in the end, I wanted to play with this one. So I used my data set that I showed you before. And I only used the data from the receiving countries, because this is considered to be the more realistic ones, because sending countries, for example, Austria doesn't know that I'm not an Austrian citizen anymore, and the UK thinks I'm living in the UK. So yeah, I'm myself kind of making this much harder. Anyway, receiving country data is better. So we used this country data. We had 9 countries. We connected them by 30 edges, depending on where they are located. The UK, for example, would have been completely lost in this whole setting. We used this data and tried to estimate the weights. And in the end, I don't know the ground truth, but here's a posterior for the node which corresponds to Germany, the marginals, or to France, and to the cost of moving from Germany to France. So you can do it, it converges. I can't tell you the ground truth anymore. And that was kind of the first try. Can we even run this and does this give us some results? And the answer is yes. However, we have to test it more on larger settings. And as I said, it was more of a toy problem. Okay, so this was work with Andrew Stewart, and we stopped there and we tried or think of trying bigger things. Still working on it, kind of time delays here. But there have been some recent developments, and one of the questions, and that's something that made a lot of sense in the following sense, is that I was always wondering about identifiability. So I showed you, okay, when it's overdetermined and underdetermined, but there is one observation which one immediately makes, and this is what we're going to work on right now. And it's also very nicely written down in a paper by Schafter and co-workers. And I should, sorry, this should be a G last night. Anyway, so we remember that my transportation map is my G plus some noise. However, and this is kind of a nice observation, is that if you observe it without noise, then your T has to satisfy your marginal constraints. So if I assume that I have no noise on my transportation map, then T completely determines P and Q, because it's from the set of admissible transportation plans. If it doesn't, then you haven't found the right solution. So now this should be G inverse, is you want to find T given C. However, I mean, this is not well defined immediately. You can find this because the T does not uniquely determine your cost. For example, if you add a constant to the cost, you get the same transportation map, so for every entry. And you can have a look at when does a cost function give you the same transportation map. And this is, as I said, these are some works by Schafto and co-workers, and they actually characterized when two matrices, so the set of matrices which can be or give you the same transportation map T. So this is what we see here on the bottom. So these are all function C's such that K, which is e to the power of minus C, so this is my Gibbs kernel, can be written as dr times T times dT, where these are my two diagonal matrices. And if you think of this, if you know how Sinkhorn's algorithm works, then these are the two matrices which calibrate your marginals. So this set corresponds to all this set of matrices. So you don't have a unique matrix. You can look at equivalence classes, but you definitely don't have unique identifiability. And so the results that I showed you were a bit surprising in this sense, because still they were fairly good. Yet we had, as I said, the perturbed case. So I didn't satisfy the marginal constraints. I always picked up the marginals fairly nicely, which makes somehow sense since the T determines your marginals P and Q. For the C, it was much harder. Yet you also have to take into account that you restrict this actually to the right equivalence class. And what they had a look at, and if you're interested, it's called probabilistic inverse transport, as, okay, what is actually a criterion to characterize this set of all matrices which are general, which give you the same T. And in the end, it's the cross ratio. So if you have, if they have a matrix A is equivalent or cross ratio equivalent to B, if all these beautiful cross ratios, looks very ugly, are the same. And this is equivalent to being able to write these two matrices as one as just dr times BDC. So that's what we saw before. So these are all the matrices which are cross ratio equivalent. So this is what they defined here. And if you want to sample, then you want to make, for example, sure that you're not jumping between all those different manifolds which are defined by these classes. So you should restrict yourself to one of those sets, and they did this very nicely in this paper. So this is this 222 paper, and I will refer to it. And we're currently looking at using similar ideas to sample. And however, we do have a bit of a different objective here. First of all, we want to be a bit more realistic. So first, what do you do if some of the data is missing? So we want to use these ideas of Schafto in the case where I have data missing in my transportation map. So now D is your Kullback-Leibler divergence. So you want to minimize the Kullback-Leibler divergence between pi, which is now my transportation map, and some data T, where I might have some missing terms, and you want to add a regularization, and you want to find the kind of underlying cost. The other thing is that is quite interesting and that we're looking at right now is what do you do if your marginal constraints are not satisfied? So what if the transportation maps and the marginals do not fit? Which in the end, if you go to mathematics, it corresponds to a generalization of OT, which is called unbalanced OT. So if you go back to OT, then you always assume mu and nu have the same mass. However, if for whatever reason mass appears or disappears, there are different ways how you can account for that. So if you go to the literature, there are 4 or 5 papers, but most of them, what you do is you add penalization terms. So these are my penalization terms tau, where the D are some divergences, and they penalize that if, I mean, this gives you the mass taken from X, if it kind of deviates from your marginal mu. The same here if it deviates from the marginal mu. So you're trying to penalize that and then minimize among all pi such that these two terms kind of don't go out of hand. And we are looking also how we can incorporate these ideas by Schafter to use that. So just to conclude, we use the Bayesian framework for inverse OT problems, and we also try to look at graph-based cost. And one has some kind of computational framework to solve these inverse OT problems, yet I think especially this for constructing sampling schemes or making sure that you stay within the same reference frame, you should do better. And yeah, we are trying to look at this kind of different problems that I showed you, unbalanced. It would also be nice to look at the continuous formulation, but you immediately run into similar problems like identifiability and data assimilation techniques. If you have for each year new transportation maps, how can you use that to update your estimates for the cost? I mean, there are, if you want to relate this to digital twins, I think for transportation networks or societal flows, you can see them as a digital twin, if I'm not mistaken now. If you want to identify or train your digital twin for some kind of network and make predictions, definitely this would be a direction to look at. And so these are the papers. As I said, this is the work with Andrew Stewart. This is the paper I reported on the very end by Patrick Schafter. And with this, I would like to thank you for your attention.
Thank you very much. Any questions? Yep.
Sorry, this is a bit obvious, I guess, but as a question, but I guess it's possible also in what you do to simplify the problem by modeling the cost Cij as just a function of I and j, like you would have attractivity of country I minus attractivity. Or,
yeah, you could, yes.
Yeah, so just two parameters, one for I, one for j. Have you thought about that? Try anything like
I mean, what, for example, what the demographs do, they have some much more simple, you parameterize the cost or kind of try to do that. Yes, this has been done. I haven't looked at it, but it would definitely be an option, yes. So.
But you could still reuse the same framework.
Yes, you could do everything.
Any other question?
Yeah. Thanks for a great talk. I was wondering about the prior. You had this, if I understood correctly, a uniform prior.
Yeah.
And on each coordinate, and then you can sort of normalize to make sure it sums to 1. That's going to become sort of less useful in large N settings, isn't
it?
Is there a way to come up with a prior that's going to generalize to that limit?
We haven't, I mean, I know that this is a very stylized assumption, and we were always thinking, yeah, what do you do if you have a better prior? We never thought into this direction yet. I'm with you that our assumption was definitely not the best one, and how to choose a good prior on the cost. One could, as you suggest, for example, parameterize the cost, then you could probably give priors on the parameters, which might be easier. However, we haven't looked at that yet.
Thank you very much again. Hey, hi everyone. So our last speaker for today is going to be Christophe Andrieux. So Christophe is a professor in Bristol, and we had to swap the talks earlier, but he did make it despite a fire at the station, so that's pretty good. So Christophe, please go ahead.
Okay, thank you. So I hadn't been to London since before the lockdown, and so far it's been a success, I should say. Okay, so I'm going to talk about how to compare Markov chain Monte Carlo methods using some inequalities, weak Poincaré inequalities, and I'm sure that many of you have heard about Poincaré inequalities, but I'll try to go through some of the basic ideas if you're not familiar with Poincaré inequalities, right? So the aim of the talk is basically to show you that we've developed some tools to quantify the convergence of MCMC algorithms to equilibrium, in particular in the subgeometric case, because there's a lot of theory in the scenario where you converge geometrically, but not all algorithms, unfortunately, converge geometrically. And if you're interested in understanding algorithms a bit better, then we think that these tools are really interesting. And I will show you in particular how we've managed to develop some kind of quantitative Peskin-Tierney algorithm and quantitative versions. And if you're not familiar with this, again, I will explain what I mean. And I will try to show you that basically these approaches, as I was trying to convince Chris earlier, is that in many ways, these approaches are very simple, right? When they work, they are extremely simple, and they are, very good complements to the minorization drift theory, through which most MCMC algorithms have been analyzed in the past. So I will motivate most of what I'm going to say with a pseudo-marginal algorithm. And again, I will explain what it is, but what is important to know is that pseudo-marginal algorithms are rarely geometrically ergodic. So that's why you need some of the tools that are there. And what I will show you is that these algorithms can be thought of approximations of good algorithms. And somehow, what I will show you is how we can somehow disentangle the effect of the approximation to the algorithm you would have liked to implement but cannot implement. And actually, we can quantify many interesting things. And there's an application to the PMMH algorithm and how to tune the number of particles you use in a PMMH algorithm. So I will start with a motivation. And so I think we're all familiar with the Metropolis-Hastings algorithm. This is just a bit of notation here. So my target distribution throughout will be denoted mu, and I will assume that it has a density. And that's what you need when you implement the Metropolis algorithm using the proposal distribution Q. And in particular, you need to evaluate the acceptance probability. The problem is that in some scenarios, the density mu is not known, and you need it to implement this algorithm. But there are fortunate situations where basically instead of mu, you can produce an unbiased estimator of mu. And the idea of pseudo-marginal algorithm, so here is my estimator of mu y, I, right, with a hat. And pseudo-marginal algorithm corresponds to just replacing the expression for mu in your acceptance ratio with an unbiased estimator, which should be non-negative, right? And this can be useful. This is also another important message. But really, the miracle is that basically in this scenario, when you've got a non-negative unbiased estimator, this algorithm is still valid if you're interested in sampling from mu. That is, eventually, under mild conditions, the Markov chain will converge to a distribution, a marginal of which, the X marginal, will be mu in the limit. So that's of interest, right? So I'm going to introduce a bit of notation just to be able to formulate some of our results later on in an easy way. And basically the main idea is that I'm going to rewrite the estimator of the probability density in this way. That is basically just as basically the true density times a perturbation W of X, which I may refer to as a weight. So that's a multiplicative noise, if you like, whose expectation should be 1, right? Because we are interested in something that is unbiased. So it can be unbiased up to a constant, but I will say unbiased throughout. That's not important. And WX should be non-negative, right? So just think of the acceptance ratio, you see, as basically being the acceptance ratio. So the acceptance ratio of the pseudo-marginal algorithm is that of the algorithm you would have liked to implement times a ratio of perturbations, right? And basically this ratio of perturbations has a negative effect on the convergence performance of the algorithm. So basically you can implement potentially the Metropolis-Hastings algorithms to more scenarios than before, but there's a price to pay. And the price to pay is that this perturbation means that let's assume that the marginal algorithm, for some reason, is geometrically ergodic. So the algorithm you cannot implement, right, is geometrically ergodic. So you may ask the question, well, is my pseudo-marginal algorithm still geometrically ergodic? And the answer is, well, not always. And basically, it's very easy for the pseudo-marginal algorithm, so the perturb algorithm, the approximation of the algorithm that you would have liked to implement, to not be geometrically ergodic. And here is in one of the conditions. That's not the only one. So what does it say? It says that basically if your weights, if your perturbations are unbounded, right, for a set of x's that is under mu has a positive probability, then the algorithm cannot be geometrically ergodic, even though the marginal algorithm was geometrically ergodic. And of course, what is the intuition, right? The intuition is that basically imagine that W is heavy-tailed. From time to time, you're going to sample a very large values of W, which means that it's going to push down the acceptance ratio compared to the marginal. And basically it's going to take ages for you to draw again a substantial large value of W that will help you escape the state. So basically that's why you observe this kind of sticky behavior, which prevents you from being geometrically ergodic, right? So one natural question is, can we actually characterize and quantify the loss in performance of the pseudo-marginal algorithm compared to the marginal algorithm? And what we are going to see is that we can do it. And basically, this is going to be formulated in terms of the tail properties of the distribution of the W's. Okay, the heavier tailed you are, the worse the algorithm is going to be. The question is, can we make this concrete and hopefully as precise as possible? So in order to, so this was the motivation, and I'm going to talk about some of the tools. And I'm going to talk about Poincare inequalities. And the main message here is that it can be intimidating in some scenarios, but basically the concept is very simple. It's only, it has only to do with derivatives. So you'll see what I mean by derivatives. So first, we have to talk about the way we are going to measure convergence to equilibrium. Okay, that is how we are going to compare the law of the Markov chain at iteration n with the actual distribution we are interested in. And the way we are going to do it is that for suitable function, and that's very often the case, what you're going to consider is the conditional expectation of f evaluated at the nth state of the Markov chain, given that you've started at x, right? So you compare this conditional expectation, which I'm going to denote in this way, right? And basically the expectation of f. And what you do is that you make this comparison over a set of functions. So here, what we are going to do is that we are going to simply consider the square distance, right? So that is the variance of P and F. And so this looks like a natural choice. And that's why basically the class of function that we are going to consider is basically L2 mu, right? And so I will use this notation for the inner product, but I won't use the properties, okay? It's just that it's a nice notation, and I'm going to use the associated L2 norm. And given the previous talks, I think you're all familiar with this kind of is basically study the speed at which basically this variance of PNF goes to 0 as n goes to infinity. And for those of you who wonder about the link with other ways of measuring speed of convergence to equilibrium, basically what you can show is that provided that mu is not too strange, basically convergence in L2 convergence will imply total variation convergence, which is maybe a mode of convergence you're more familiar with. Right, so how does one study this type of convergence to 0? And let's start with a geometric case, because that's simpler. And basically the main idea here is just to look at what I call the discrete derivative. That if we look at the effect of applying P on G, which is centered, minus G, right, D square. So that's like a derivative. And basically, my claim is that we've got a geometric rate as soon as this derivative, of course, is less than a constant times basically the function we've started from, right? Or the norm of the norm square of the function we started from. Why? Because if we reorder the term, we get this inequality, and we see that we get a contraction, right? Okay, so basically this quantity, this discrete derivative is so important that it has a name, right? And I'm going to denote it this way, and there's a good reason for this. And it can be in terms of the inner product, it can be written in terms in this way. So here, what is strange is maybe the P star, but most of you will probably know what I'm talking about. This is the adjoint. This is a quantity related to, so if you know what it is, you don't need to read anything. If you don't, basically it's another Markov chain that is related to P that I have to write down here to say things that are not too wrong, but basically we are going to do everything we can to avoid having to deal with it, right? So that's the main message, right? And basically what is important is, so the minus the discrete derivative or the is going to be the quantity that we are going to be interested in. And what is a strong Poincare inequality is when you've got basically this type of inequality, right? So remember, minus E is the drift, if you like, that you're going to get in one step by applying the Markov chain. And what you want is basically minus the drift to be lower bounded by where you started from. And that is going to ensure that you're geometric. So basically, you get geometric convergence in the light of what I said earlier, very, very easily if you've got this inequality. And that's a strong Poincare inequality. And basically, this is basically what is described in Field's paper in the 1991 paper. So for those of you who are familiar with a continuous time setup, basically here you should put minus the generator, right? And there it's really a derivative that you're dealing with, right? So unfortunately, the Dirichlet form of P star P is very often intractable because here what you've got to deal with is if you like, the composition of two Markov transition matrices. And in practice, it means computing various integrals or estimating them. And this may be tricky, right? What we would prefer is to have to deal with the Dirichlet form of P, right? So that is basically just one kernel. And there are various reasons for this. So first, I don't have to deal with the integral or expectation that is involved here, but also there's a nice expression, okay? So you can basically rewrite the Dirichlet form of P in this nice form, right? And which is classical, but super convenient and very important in practice. And basically, if you can establish something that looks like a Poincare inequality, but now for the Dirichlet form of P, right? It doesn't have a clear interpretation in terms of discrete derivative, by the way, right? If you can establish that you've got this thing, this inequality like this, that would look simpler because actually this variance of F, remember F is typically centered, basically admits also an expression of this form. And you see that if I want to establish what is on the left-hand side here, basically it's a matter of comparing these two integrals, right? And you see that if you can compare somehow the mu times P with the mu times mu, then basically there's a chance you may be able to establish this inequality. And there's one toy example, but actually I'll show you that there's an actual example where this is satisfied, and there are others actually. Basically, if you assume that P is lower bounded by the invariant distribution in this sense, that is a constant such that the probability of being at any X and jumping into A is lower bounded by a constant times the probability of the invariant distribution, then it's not very difficult to say that this Dirichlet form of P is going to be larger than the Dirichlet form of the perfect sampler. This is what we are dealing with, right? And basically, so that's this looks like a toy example, but that's one of the key ideas of all the things I'm going to talk about. That is basically we are going to rely on this kind of identities and this kind of inequalities in various forms. And we are going to deduce things. So what about the issue between P star P and P? Basically, what I'm going to tell you is that I'm going to always talk about P star P, but basically with simple additional conditions that are not artificial, that you can check in practice. Basically, you can very often show that the Dirichlet form of P star P is lower bounded by basically something that involves the Dirichlet form of P only, right? Under mild additional assumption. And here is a very simple example, which says basically wherever you are, there's a probability of at least epsilon that you're going to stay where you are, right? So that's a holding probability. And that's one trick that people have used in the literature, the classical literature, to address basically this issue. And in fact, so I won't have time to go over this, but we've weakened significantly thanks to the theory, this kind of conditions, right? So basically, I'm going to talk mainly about P star P, but basically the trick is that actually in reality, we're going to work on P and we will have an additional assumption, which I'm not going to discuss much here. Right, so what about the pseudo marginal algorithm? So you remember this was the acceptance ratio, acceptance probability, which involves the acceptance ratio of the original algorithm we would have liked to implement it, but there's a perturbation. So one thing one can show is that actually in the scenario where there is a W bar such that basically, so what this says is that the WX's are uniformly bounded, right? So wherever X is, basically WX cannot exceed a given value that is finite. And in this case, what you can establish is that the Dirichlet form, so P tilde is the pseudo-marginal algorithm. And basically you can lower bound the Dirichlet form of P tilde star P tilde by the Dirichlet form of the algorithm you're actually interested in, right? You would have likely implemented, but there's a penalty, okay, which is related to the size of your largest weight, if you like. So some of you may have noticed that P tilde star and P star don't live on the same space, but there's a way of making this rigorous. It's just I don't have time to explain it. Okay, so that you can do. And so why is this interesting? So you see, we are comparing the Dirichlet forms. Okay, so minus the discrete derivatives of two Markov chains. Right? But now if I assume that my good algorithm is actually good, so it satisfies a strong Poincare inequality, it converges geometrically, right? Then you see that basically I can chain the Dirichlet forms, okay? So that's very simple. So basically what you deduce is that if my algorithm P converges geometrically because it has a strong Poincare inequality, then thanks to this inequality here, I can deduce that the pseudo-marginal algorithm is also geometrically ergodic, but there's a penalty. And you see, one nice thing is that we can disentangle the effects of somehow of the algorithm we are trying to approximate and the effect of the approximation, right? So that's nice, but a natural question is what happens actually when your weights are potentially unbounded? And we know that the algorithm is not going to be geometrically ergodic. So this cannot hold for a W bar that is finite, right? So that's why one needs to move towards weak Poincare inequalities, right? So what is the idea? So strong Poincare inequality, you remember the discrete derivative, we assume that basically it was less than what I would call a drift, minus CP and G square. So basically something that is proportional to where you're coming from. And a natural question is to say, well, actually, if this discrete derivative is now less than G square to the power alpha, where alpha is larger than 1, okay? So my claim is that despite the fact that alpha is less than 1, this is a weaker drift. Because of course, if G, the norm of G square is small, this is even smaller than G square, right? Because of the power larger than alpha. Okay, so basically you see that if I get a condition on my Dirichlet form that involves something of this form, then I cannot get geometric ergodicity, but something that is weaker. So because the more I converge, the more I've got drift, right? That's what this says, right? So this sounds like a good idea, but it doesn't work. And one reason for this is on the last display line is that, of course, if the norm of G is sufficiently large, basically the right-hand side is negative, whereas the left-hand side should be positive. So that's not the right way to formulate this, but you can adapt it in a way which makes everything works and basically follows along the same line as before. It's still that idea of discrete derivative. It's just that you've got to introduce an additional ideas. So first, basically, you cannot have you cannot consider subgeometric convergence for any function in L2, right? So that's the first message. So you've got to restrict the set of functions. So I don't have to time to explain this, but there's a good reason. So you've got to filter out suppress some of the functions in L2 mu, and that you do through a functional, which we've called a sieve, which should have some properties that make it look like the square of a norm, of a functional norm. So these are the properties. So you can think of phi of G, typically the oscillation square or the infinity norm. You can be more general, but there are many connections between various choices of phi, but I don't have time to go over this. And the right formulation, which was suggested by Liggett, but as I discovered in Finland, was in fact suggested by Stroop to him, is in this way. So again, you get something that you see still looks like a strong Poincare inequality, right? But now you've got to involve the ratio of your Dirichlet form with your sieve function, etc. And basically that was what is suggested. And in fact, you can generalize. That is basically, you just said that your Dirichlet form divided by phi of G is larger than K star of the L2 norm of G squared divided by phi of G, where K star should be convex and satisfy some properties that I don't have time to detail. And basically the strong Poincare inequality corresponds to a particular case where K star is actually linear. Right? So here again, we get something where we say something about the discrete derivative of the quantity I'm interested in. Right? So once you've got this equation, condition 1, which should hold for any G, with a few steps, it's not direct. Basically, what you can show is that you get that the discrete derivative of Pn plus 1, or the discrete derivative of Pnf divided by the sieve, basically, is less than minus K star where you were coming from, basically. And what is nice is that basically a sequence that satisfies this kind of inequality. So if you imagine that this here is Vn plus 1, this is Vn. So this looks like a sequence of this form. Basically, you can easily find an upper bound on the sequence of Vn's, and it is given by this integral, and you've got to invert the integral. So provided that you can estimate this integral and its inverse, basically you can get the rate of convergence you were interested in, right? So the problem is that this is all nice, and this is intuitively satisfying because it all makes sense. It's related to discrete derivatives, but the question is, how do I establish this condition 1 in the real world? And basically, whereas this is a very important step, basically this is not very practical, right? And what I'm going to show you is now a virtually equivalent formulation of equation 1, which is actually linear, right? And is going to be the one that you use in practice in order to establish this condition 1. Okay, so we've got the strong Poincare inequality, the generalization for the subgeometric case. And basically what you can do. So for those of you who would know about these things, basically it's related to complex conjugate of functions, etc. Basically, you can linearize this condition in this way. That is, basically, you just say that instead of having an inequality for fixed parameters, you should have this type of inequality where, again, the variance of f is on the left-hand side and the Dirichlet form is on the right-hand side of the inequality. But now you see we've got things that are not constants, s and beta s. Basically, this inequality should hold for any s and for any f, right? So basically, we've suppressed the nonlinearity that was brought in by k star. We've replaced it by a condition where you've got a function beta s that is going to be involved in this inequality, and this should hold for any s. So for those who are familiar with convex functions, basically you're looking at tangents of your function, right? And you're looking where it crosses the y-axis. That's what it is doing. But what is important is that you need now to identify this function beta s. And it turns out that this is relatively easy in many scenarios that would otherwise look extremely complicated, right? So think about beta s, for example, as being a function of this form, okay? Right, and basically this formulation and these formulations are virtually equivalent, okay? It's just technicalities, right? So what is going to happen in practice is that in practice, you've got hope that you can work with this generalized super Poincaré inequality. So now it's a weak Poincaré inequality. You don't need to understand these equations. This just says that basically there's a way of going from beta to k star. And earlier I told you once I've got k star, I can get the rate of convergence. So there is a route, okay? And although sometimes you cannot do the calculations exactly, okay? In many scenarios, you can upper bound, lower bound, you know, this kind of things, and find estimates of f-1 and get the rate of convergence, right? And here are just some examples just to show you that you can do it. So if you've got beta s of this form, then you can find a rate of convergence that is polynomial, although it's not polynomial. If beta s is of this form, you find this kind of sub-exponential rate of convergence, okay? And one thing that is interesting from an intuitive point of view is that the faster beta decreases to 0, the faster your convergence is going to be, okay? And on the contrary, the longer it takes beta to reach 0, the slower the rate of convergence is going to be. So I've got another 10 minutes. That's right. So I think I've got time to go through this example. So example of this, application of this to a toy example. So the independent metropolis Hastings algorithm, which corresponds to the scenario where, so we know mu here, okay, there's no pseudo-marginal marginalization. The proposal distribution does not depend on where you are, right? And I'm going to use this notation. So you see that I can group mu and qy together in this way. And I'm going again to talk about these weights. Okay, so basically the ratio of pi and the proposal distribution, okay, evaluated at the same point. So what is known about the independent metropolis Hastings algorithm is that actually it is geometrically ergodic if and only if the weights are uniformly bounded, right? So that's an old result. And in fact, what I can show you immediately in a few lines, in an application of some of the ideas that I've told you about earlier. So it's not very difficult to establish that actually the transition probability of the metropolis, the independent metropolis Hastings algorithm satisfies, you remember the condition I mentioned earlier, except it was a CP here, but here we are less than, we are minorized by the invariant distribution times a constant. So now if I look at the Dirichlet form of P, and believe me, in this case, you can go to P star P very easily. okay? Because for those of you who know, the IMH is positive, right? So there are no problem. So you see that here, I immediately get this lower bound, right? Because of this. And as a result, I've got a strong Poincare inequality for P, right? So with an additional condition, I'm going to get geometric convergence. So now what happens if W bar is not bounded? Basically, in this case, and I'm going to try to show you in a few lines, at least the main ideas of how these things work. Basically, what you can show is that beta S is upper bounded by 2 times, you see, the tail probability of your weights, right? So the interpretation is super clear, you know, so basically the more variability in your weights, the more heavy tail the distribution is going to be, the slower the convergence is going to be. And that corresponds to our intuition, right? So that's the thing. And then of course you can upper bound this using Markov's inequality. And so if you've got moment conditions, you can immediately translate them into rates of convergence, which are not necessarily optimal. It depends on how correct your assumptions on the weights, of course. So what is the idea? So probably you won't have enough time to absorb all the details and whatever, but what I want to show you is how the strategy may work, right? And basically the first thing is that you remember earlier I told you that the IMH satisfies, when the weights are uniformly bounded, satisfies a minorization condition, right? So the question is what happens when the weights are not uniformly bounded? In this case, basically what you can show is that, yes, you're not uniformly lower bounded, right? Because now what was W bar earlier depends on both X and Y. Okay, so you can establish this, that's just algebra. And basically then the next idea that is really useful and very easy to apply with these techniques is that basically what you're going to do is that in your integrals, you're going to split all your integrals into a part where you've got something that looks like a strong Poincare inequality, so the good set, and the bad set, right? So that's how things are going to work. So let's see how this is going to work. So obviously here, the good set is going to be the set where basically this is bounded away from 0, right? So that's why I introduced this good set, A, which is parametrized by S. That's not by chance, right? And that's the set where now I call this quantity here, I call it epsilon x y, and I'm going to assume that it's larger or equal than 1 over S, where S is not 0, right? So I'm bounded away. So I have a minorization condition. So basically, I know that on this set, I've got a strong Poincare inequality, and I'm going to use this. So I want to establish a weak Poincare inequality. So I start with the left-hand side with a variance of F, right? I use this formulation. And now what I'm going to use is this, right? So I take S to the left-hand side. So mu is less than S times P. That's what I've said here, right? And you see that this looks almost like S times the Dirichlet form of P, right? So this looks like, this looks like a strong Poincare inequality, but for this set, A of S, right? And then we've got to deal with the complement, okay? With the complement of the set. So the way we do it, so for example, and there are various choices, but here, if you assume that the oscillations of F are bounded, you can upper bound this integral with the oscillations of F times the probability of this complement set. So that's how you get to this line, and that's how you get here, right? And basically, this is your beta S, right? So you see the beta S somehow controls basically the bits where you don't satisfy a strong Poincare inequality. So that's one way of dealing with it, but you see that you have to be parametrized by S because there are many such sets, okay? It's just that in the limit where S is equal to infinity, you don't know how to deal with. You don't have a strong Poincare inequality. So you look at it for all S. And that's a generic strategy. So I won't have time to show you many other examples of this, but basically that's a generic strategy that turns out to be super efficient in many scenarios. So now I'm going to show you an extension of these ideas, and I'll go through this very quickly, but I'm sure that you will understand how these things work. So far we've discussed this kind of inequalities. And by the way, the strong Poincare inequality corresponds to the scenario where beta drops to 0 at some point. Okay, so that's one, so I'm covering everything here. So one idea that we've suggested is actually to introduce this kind of inequalities. So we've got two Markov chains, P1 and P2, that share the same invariant distribution mu. And somehow you see we are comparing their drifts. That's what we are doing here, right? And of course, this here is just a special case, but that's not important, okay? But is it clear what we're going to do? And of course, what we want to do at some point is to compare the pseudo-marginal and the marginal algorithm. So this is going to be the good algorithm, the marginal algorithm, and this is going to be the perturbation, right? And the perturbation, we are going to measure the effect of that perturbation through the beta. And I'm not going to show you the exact calculations, but they are very similar to what I showed you in the case of the independent metropolis Hastings algorithm. So just to show you, but it's sort of obvious how you're going to use these things in practice. So let's assume that I've got this condition that my algorithm on the left-hand side satisfies a strong Poincare inequality. Then of course you get this inequality, right, for P2. So basically what we deduce is that P2 satisfies a weak Poincare inequality. And I know the constants, assuming that I had these conditions. So you can generalize this, of course, to the scenario where your good algorithm satisfies a Poincare inequality and relative to P1, P2 satisfies a weak Poincare inequality. You can combine them. There are some formulae, some are very nice, such as this formula, but you can imagine how it works. It's just a matter of calculations, right? Okay, so just very briefly, and this is how we apply this to pseudo-marginals. What we can show is if you've got an inequality of this type between a P2 and a P1 that leave invariant distributions, then automatically you get this kind of inequality on P1 and P2, right? And again, trust me that you don't have to worry about the P stars in here. What is important is to be able to establish this, right? And you see that between the pseudo-marginal and the marginal algorithm, we can establish this type of inequality, okay? And that I wanted to skip. And basically for the pseudo-marginal algorithm, what you can do is actually establish this kind of inequality. So this is my P1. This is the marginal algorithm embedded in the joint space, right? Because I mentioned earlier that there was an issue. This is the pseudo-marginal algorithm. So I can somehow relate the two rates of convergence. And what is interesting is that here we've got an expression for the function beta s, which characterizes the degradation in performance of the pseudo-marginal algorithm. And what is nice is that this is clearly has a clear interpretation. Okay, so that's the invariant distribution. This is the tail distribution of W multiplied by W. And basically what matters are the tails of that distribution, right? So if you've got some characterization of how heavy tail the distribution is, you can get a bound on beta s and you can deduce a rate of convergence. So we've applied this to the, and I'm going to stop in 30 seconds. We've applied this to the PMMH algorithm, which is a pseudo-marginal algorithm for hidden Markov models in situations where you use a particle filter to estimate the likelihood function. So basically you plug in a random estimator of the likelihood function in your Metropolis Hastings algorithm. So particle filter, we've got to choose the number of particles in an optimal way. And there's been some work on this. And basically, so we found various things using approximations where the number of particles and the length of the time series are long enough. And so we find a rate of convergence, you see, in terms of the marginal algorithm, right, again, and the variance of your, or the constant involved in the variance of the particle filter. So we've got an upper bound. To be honest, we don't know how good it is, but with this, what we've done is that we've looked at the asymptotic variance of the so the variance, the asymptotic variance of n times the variance of ergodic averages of the Markov chain evaluated at some functions. And with taking into account the cost, we end up with a weighted function, okay, which takes into account the cost involved by taking n particles. So this is your cost. And basically, we get an optimum around 1, which corresponds to earlier values that were found in the literature using completely different methods. But there's another discussion in the paper about what happens with the rate of convergence, where basically you find a different answer to what you find when you're interested in the asymptotic variance of ergodic averages. Thank you.
Great, thank you very much, Christophe. Any questions? Yeah.
Just to be sure, in the theorem 11, you assume that your estimate as a log normal distribution, right?
Yes.
Which is not true in general, but it just simplifies the analysis.
Yeah. It's just.
So you said it's a completely different analysis of a problem, but you make the same assumption as that it's a log normal, right? Because the paper by
they make the same assumption.
For the log normal, I mean, this paper with Arnaud Doucet,
and
where they find this optimal.
It's using the log normal approximation. Yeah. So it's not the exact algorithm we study.
It's too hard to study, I guess. Yeah. Okay.
Any other question?
Yeah, that's a quick one. Thanks, Christophe. I'm trying to draw an analogy in my mind between what people do to analyze continuous time Markov processes. And in that world, you tend to fix your algorithm and then ask for what targets the algorithm mixes quickly. And the assumptions that you make then correspond to sort of geometric properties of the distributions that you're trying to sample. So is there a geometric interpretation for some of these inequalities that you've presented?
I'm not sure that I understand the question, because you said that your invariant distribution was not fixed.
So sorry, so if I were to write a paper analyzing the overdamped Langevin diffusion, I would make some assumptions which would refer to the geometry of the distribution that thing is targeting. And whereas in this case, you're saying, well, okay, in some sense, the distribution you'd like to sample is fixed and you're comparing different algorithms to sample from it. So I didn't get that same geometric interpretation of the assumptions, but is it possible to get one?
Right, so you're right that here I mean, the main results that have to do with a comparison, I don't think that there is a clear geometric interpretation, but if your question is, can you relate geometric properties of the target distribution to a rate of convergence of your Markov chain, of your MCMC algorithm? So we've got the other paper where basically, for example, we study the random walk metropolis algorithm in large dimensions, and in particular, we studied the scaling properties of the spectral gap, and how you should scale the variance in your algorithm in order to get the best rates for your spectral gap. And indeed, in this case, we've been able to establish these results using some very specific geometric properties of the target distribution, or properties of the target distribution.
So you have applied your results now to the area where you've worked a lot with pseudo-marginal. Can these results also be applied when, for example, the drift comes through numerical discretization? Say if you have some target and then of an infinite dimensional thing that you can't really target, and then you have a finite element discretization involved or some other discretization involved.
Yeah, so there's one thing that we haven't really resolved. We discussed it a bit in the paper, is that I guess in the scenario that you're discussing, the invariant distribution changes, right? And although we've got some ideas, we haven't been able to really handle that scenario well. Okay, so here it was very important to that the invariant distribution remains the same. And there's a small discussion about what happens if the invariant distribution changes. And I don't know if it is the case that we don't know how to do it or whether it's impossible.
Okay, let's thank Christophe again.
Yeah. Thank you.